What if the emptiest places in the universe weren't empty at all? What if space itself, the black silent vacuum between stars, was hiding something vast? Not stars, not planets, but something stranger, something deeper, a hidden energy that never stops moving, even when everything else does. Today, we're diving into one of the strangest ideas in all of modern physics. A truth that defies common sense, but has been measured again and again. That even in a perfect vacuum, in the cold, airless stillness of deep space, there is energy. Motion. It's called zero-point energy, and once you understand it, your idea of nothing will never be the same. Before we begin, I want to ask you something. Where in the world are you watching from right now? And what time is it there? Morning, night, or somewhere in between? Drop it in the comments. I love seeing how far this community stretches across the planet. And if you enjoy these slow, deep science journeys, the kind of content that takes its time, please consider subscribing and helping us reach. Every single sub keeps this channel going and keeps the long-form science alive. All right, let's begin our journey into the invisible energy of nothing. Chapter 1. What is empty space? Really? They say nature abhors a vacuum, but that statement barely scratches the surface. For most of us, the term empty space paints a clear picture: vast, black silence between stars, untouched by sound, matter, or movement. A perfect stillness, a cold nothing. That is what we are taught to believe. That space, in its most extreme form, is a barren void, a backdrop against which the real action of the universe unfolds. But that assumption is wrong. Profoundly wrong. Because, as science now shows, what we call empty is anything but. To understand how, we have to first shed our everyday understanding of nothing. In classical physics, the physics of Newton and the intuitive world, a vacuum is simply a volume of space completely devoid of matter, no particles, no atoms, no air, no dust. A vacuum is where nothing exists. It's how we describe the space between the Earth and the Moon. It's what we imagine between galaxies, where stars grow faint and cosmic silence reigns. But quantum physics has forced us to reimagine everything. It tells us that even in the most perfect vacuum, even in a sealed, shielded container cooled to near absolute zero, where no light or matter remains, there is still energy. Tiny, jittery, ever-present fluctuations ripple through that supposedly silent space. These aren't theoretical guesses or imaginative stretches. They're measurable, detectable, provable. This ever-present hum of energy in nothing has a name: zero-point energy. To begin our journey into one of the strangest and most important concepts in modern physics, we must ask a bold question. Not just scientifically but philosophically. What is space without matter? And can nothing ever truly mean nothing? The story of how scientists came to doubt the emptiness of empty space began more than a century ago, as they probed into the world of the very small. When quantum mechanics emerged in the early 20th century, it wasn't just a new model of particles, it was a radical rewriting of what particles even are. And more importantly, what reality is when you look close enough. Werner Heisenberg, one of the founding minds of quantum theory, introduced a principle that would change everything: the uncertainty principle. It stated quite simply that certain properties, like a particle's position and its momentum, can't both be known exactly at the same time. The more precisely you know one, the less precisely you can know the other. This isn't a matter of bad instruments or human error. It's not a limitation of our tools, it's a fundamental limit written into the fabric of the universe. So what does this mean for the idea of emptiness? Well, take a simple example. Imagine a particle trapped in a box, perfectly still. Classically, you could say it has zero momentum, and you know exactly where it is. at rest, unmoving. But quantum mechanics says that's impossible, because if the particle were truly at rest, with zero momentum, we'd have perfect knowledge of its energy. Combine that with knowing its position in the box, and you've just violated Heisenberg's principle. Nature forbids it. So even in its lowest possible energy state, even in the ground state, the particle must retain some movement, some jitter, some residual energy. This is the zero-point energy. It is the energy that remains when a system is cooled down as far as it can go, to absolute zero, the coldest temperature theoretically possible. And yet, even there, motion remains. Now zoom out from the particle in a box, and think bigger. What if we applied that same logic not just to one particle, but to space itself? In quantum field theory, every type of particle corresponds to a field that stretches across all of space. These fields, for electrons, quarks, photons, are the true fundamental objects of reality. What we think of as particles are just tiny ripples or excitations in those fields. Imagine the surface of a calm lake. A small splash sends a ripple through the water. That's your particle. But even when no splash occurs, even when the lake seems perfectly still, there's still subtle motion. Tiny, jittery waves dance across the surface, too small to see but undeniably there. That's how physicists see space. A calm lake, made up of energy fields, always moving, always fluctuating, even when no visible particles are present. This picture of a constantly vibrating vacuum, this invisible ocean of motion, challenges everything we thought we knew about the emptiness of space. It tells us that the vacuum isn't a place where nothing happens. It's a place where everything happens, all the time at the smallest scale possible. And this brings us to one of the most elegant and eerie demonstrations of zero-point energy ever discovered. The Casimir Effect. In 1948, Dutch physicist Hendrik Casimir proposed a strange idea. If you take two uncharged parallel metal plates and place them a tiny distance apart in a vacuum, with no particles between them, they should experience an attractive force pulling them together, not because of static electricity, not because of magnetism, but because of the energy of the vacuum itself. According to quantum theory, the vacuum is full of virtual particles, particles that pop in and out of existence too quickly to be directly observed, yet real enough to exert force. Between the plates, the size of the gap restricts which fluctuations can exist, like only certain sound waves fitting inside a flute. Outside the plates, the vacuum fluctuations are unrestricted. The result? A subtle pressure difference. There are slightly more vacuum fluctuations outside the plates than between them, and this imbalance creates a force gently pushing the plates together. This force has been measured. It's tiny, almost unimaginably so, but it's real, and it's not coming from air or heat or any classical interaction. It's coming from nothing, from the energy that lives in the vacuum itself. Now pause and consider, because if you accept that empty space isn't empty, that it has structure, energy and behavior, then everything else changes. Suddenly the universe is no longer a set of objects floating in a vast emptiness. It is an intricate, ever-moving web of invisible fields, vibrating even in their quietest states. And those vibrations, those zero-point fluctuations, aren't just mathematical noise, they're physical. They can affect atoms. They shape the way forces act. They play a role in why matter behaves the way it does. Some physicists even speculate that this vacuum energy might be responsible for some of the universe's greatest mysteries, including the dark energy driving cosmic acceleration. But we're getting ahead of ourselves. For now we sit with a truth that feels almost mystical, and yet is cold, hard physics. That space, empty space, is full. That nothing, pure, perfect, absolute nothing, is not just unstable, but impossible. And that every point in the universe, no matter how quiet, no matter how cold, hums with an invisible energy that has always been there and may never go away. In the chapters ahead, we'll explore how scientists discovered this, why it matters, and what it could mean for the future of physics, technology, and maybe even the fate of the universe itself. But it all begins with this unsettling realization. What we call nothing is the most restless thing of all. Chapter 2. The birth of quantum fluctuation. If empty space is not truly empty, then the next question is inevitable. Where does this restless energy come from? How can something appear in the absence of matter, light, and heat? To understand that, we must travel back to the very roots of quantum theory, to a time when physicists first began to suspect that the world they thought they understood was not as still or predictable as it appeared. The early 20th century was a time of radical change in science. Classical physics, with its orderly laws and clean predictions, had ruled confidently for centuries. Newton had described gravity, Maxwell had unified electricity and magnetism, thermodynamics had explained heat. The world seemed complete, knowable, mechanical, and governed by clear, objective rules. And yet something strange was happening. Experiments on light, on atoms, on the photoelectric effect, they were revealing cracks in the classical framework. At the atomic level, reality did not behave the way it was supposed to. Energy came in packets, not flows. Electrons didn't orbit like planets. They jumped. Light was sometimes a wave, and other times a particle. Nothing made intuitive sense anymore. This was the birth of quantum mechanics, a theory so powerful, yet so strange, that even its founders admitted they did not fully understand it. But one thing quickly became clear: the world was not still. It was never still, even in its quietest, coldest state. Even when you stripped away everything measurable, something remained. A flicker, a hum, a restlessness at the heart of matter itself. That hum is what we now call quantum fluctuations. The tiny momentary changes in energy that occur everywhere, all the time, even in the most perfect vacuum. It starts with one of the core ideas of quantum theory. Energy is quantized. That is, energy doesn't come in a smooth, continuous stream. It arrives in discrete packets, like rungs on a ladder. You can't have just any amount of energy. You can only have certain specific values. And when a system is at its lowest possible energy, when all the motion you can take away has been taken away, it doesn't go to zero. It reaches the bottom rung, but that bottom is never truly flat. This is the 0 point, the lowest possible energy that a quantum system can have. It's not a lack of motion. It's a permanent, inescapable jitter. Why does this happen? Because of a principle we met before: Heisenberg's uncertainty. This principle doesn't just apply to particles bouncing around in space. It applies to energy and time as well. The shorter the time frame you observe, the more uncertain the energy becomes. And the result is that for incredibly brief moments, energy can appear where there was none. It can pop in, exist for a flash, and vanish again, all without violating the laws of physics. This is not a metaphor. It is not poetic language. It is the actual prediction of quantum theory, and we have measured its consequences. In 1947, a physicist named Willis Lamb conducted an experiment with hydrogen atom. He found that one of the energy levels in the hydrogen atom, a level that was supposed to be fixed, had a slight shift. A tiny change, just enough to raise questions. And that shift was caused by the interaction of the electron with the vacuum fluctuations of the electromagnetic field. In other words, the atom was being pushed by empty space. This became known as the Lamb shift, and it was one of the first concrete signs that the vacuum is not truly passive. It is not a dead background. It interacts, it moves, it pushes. But perhaps even more dramatically, quantum fluctuations can create virtual particles. These are not particles in the ordinary sense. They do not live long enough to be measured, but they flicker in and out of existence, borrowing energy from the vacuum, then disappearing again before nature calls the dead. This is allowed because the uncertainty principle permits such brief violations, so long as they happen quickly enough that the borrowed energy is returned almost instantly. These virtual particles are everywhere. They fill all space. They are constantly forming and vanishing. They may even play a role in the forces between particles. Some interpretations of quantum electrodynamics, the most precise theory ever tested, suggest that the force between two electrons arises from the exchange of virtual photons, fleeting particles born of vacuum fluctuation. So when you hold your hand above a table and it doesn't fall through, you are not just feeling the repulsion of solid matter, you are feeling the whisper of quantum fields and the ghost trade of virtual particles flitting between atoms. This picture of the vacuum as a sea of fluctuations, a foam of momentary existence, is not a wild speculation. It is the foundation of quantum field theory, the framework that underpins the standard model of particle physics. In this model, every fundamental force and every particle is a manifestation of an underlying field. The electromagnetic field, the electron field, the quark field, the Higgs field, each fills all space, each vibrates, and even in their ground states, when they are at rest, when they are as empty as they can be, they still fluctuate. This is the birth of quantum fluctuations. This is where zero-point energy begins, not in some esoteric place, but everywhere, not in stars or galaxies, but in the emptiness between them, in the space between atoms, even in the space between your thoughts. If such a thing could be measured, there is no such thing as silence. Not at the quantum level. There is no stillness, no true zero, only the relentless motion of fields and fluctuations, forever alive, even when nothing else remains. Some might ask, if this energy is everywhere, why don't we see it? Why doesn't it explode into visibility? Why doesn't it overwhelm us with light, or gravity, or force? That question leads us into one of the deepest mysteries in modern physics, a mystery so profound that it threatens the very foundation of our understanding. Because when physicists try to calculate the total energy of the quantum vacuum, the sum of all these fluctuations, across all the fields and all the frequencies, they get a number, a huge number, a number so large that, if it were real, the universe should have torn itself apart in the instant it began. The pressure from the vacuum should have driven space-time into collapse or infinite expansion. But that didn't happen. The universe is here, it is stable, and the actual measured value of the vacuum's effect, in the form of what we now call dark energy, is vastly, vastly smaller than the predicted amount. This is called the cosmological constant problem, and it remains unsolved. But it is intimately connected to quantum fluctuations and to the puzzle of how something can be so energetic, yet so hidden. In the chapters ahead, we'll explore that puzzle more deeply. We'll look at how scientists try to reconcile theory and observation. We'll ask whether zero-point energy can be extracted, used, controlled, and we'll confront the strange idea that this invisible sea, this ocean of jittering fields, may be the truest foundation of reality. But for now, let us stand in awe of what we've uncovered, a vacuum that moves, a stillness that sings, and a universe where even the most perfect silence is never truly quiet. Chapter 3. The Quantum Harmonic Oscillator. If zero-point energy is the heartbeat of the vacuum, then the quantum harmonic oscillator is its pulse. It is here, in this deceptively simple model, that some of the most profound truths about the energy of nothing first come to light. And though it may sound like a mechanical term, dry, mathematical, buried in textbooks, it is in fact one of the most beautiful, elegant, and essential tools in all of quantum physics. To understand why, we must begin with motion. specifically with vibration. Think of a pendulum swinging back and forth. Think of a mass on a spring, bouncing up and down. Think of a child on a swing, pushed, released, returning to center. These are all examples of harmonic motion, a rhythm the universe seems to love. At the core of it is balance between force and inertia, between displacement and return. Now take that concept, a simple mass on a spring, and shrink it down to the scale of atoms. In the quantum world, everything vibrates: electrons, atoms, entire molecules, all trapped in invisible wells of potential energy, all swaying and bouncing, unable to come fully to rest. This is where the harmonic oscillator enters the scene. It is a model, a mathematical framework that describes these repeating motions, and it becomes even more powerful when merged with quantum theory. In classical physics, a harmonic oscillator can have zero energy. Imagine a ball resting perfectly at the bottom of a bowl. It sits still. The system is at rest. But quantum mechanics forbids this. Even at its lowest energy level, its so-called ground state, the oscillator cannot be completely still. There is always motion, always uncertainty, always a ripple, a sway, a flicker. Because if the particle were perfectly still, its position and momentum would be known with total precision, a direct violation of Heisenberg's uncertainty principle. And so the system must retain a sliver of energy, a minimum, a floor that cannot be crossed. This is not just true for atoms or molecules. It is a rule written into the architecture of all quantum systems, every field, every oscillator, every so-called empty point in space. The quantum harmonic oscillator is not just a model. It is the scaffolding on which the vacuum itself is built. Every quantum field, the electromagnetic field, the electron field, even the Higgs field, behaves like an infinite collection of these oscillators. Each point in space can be thought of as a tiny spring, jittering with zero-point motion, never silent. And when you add them all together, when you let them stretch across the whole of space, you find that the vacuum is alive, pulsing with invisible energy, everywhere, always. This isn't speculation. It's the mathematical consequence of quantum field theory, the most accurate and successful framework in physics. It's what gives rise to the Casimir Effect, to the Lamb shift, to measurable deviations in real atomic systems. It is not just theory. It is experiment. And it begins here, with the oscillator that never stops moving. There is something haunting about this, something almost poetic, that the universe, even in its quietest places, contains music. Not the music of air, or sound, or instruments, but the vibration of field, a harmony not heard, but woven into the mathematics of being. Even if you could remove all matter from the cosmos, all stars, all gas, all dust, this background energy would remain, a sea of oscillators, trembling just above nothing. Physicists often describe this as the vacuum state, the lowest possible energy configuration of a field. And yet even this lowest state is teeming with motion. Why? Because energy in the quantum world is not a flat line, it is a staircase, and the vacuum stands on the first step. It's tempting to imagine this energy as useless, trapped, inaccessible. After all, it's everywhere, but we can't scoop it up, can't tap it with wires, can't see it with our eyes. But that hasn't stopped scientists or dreamers from trying, because if the vacuum truly contains energy, vast amounts of it, then perhaps it could be harnessed, perhaps it could be extracted, perhaps it could fuel engines, or power spacecraft, or bend the fabric of space-time itself. Some have called this idea fringe, others heretical, but it begins here, with the undeniable truth of the quantum harmonic oscillator. It is in this model that the door to zero-point energy is first cracked open. It is here that we see, with mathematical clarity, that the vacuum cannot rest. And it is here that science begins to flirt with something deeper. The idea that reality at its core is built not from objects, but from vibration. That notion changes everything. It changes how we think about particles, not as little balls, but as wave packets, ripples in a sea. It changes how we think about space, not as a void, but as a dynamic, energized medium. And it even changes how we think about motion. Because if everything vibrates, then even stillness is an illusion. There is no true silence in the quantum world, only motion too small to see, only energy too subtle to feel. But it is there, always, at the base of everything. The whisper of the vacuum, the song of the oscillator, the breath of a universe that never ever stops. And so the quantum harmonic oscillator, far from being a classroom abstraction, becomes a gateway. It invites us to look again at nothing and find in it the deepest something of all. Chapter 4. Heisenberg's uncertainty principle at work. If there is a single idea in quantum physics that shakes the very foundation of certainty, it is this: the more precisely you know one thing, the less precisely you can know another. This is not just a philosophical riddle or a temporary gap in our knowledge. It is a hard, unbreakable rule, a law etched into the structure of reality itself. And it is the reason why zero-point energy exists at all. This idea, known as Heisenberg's uncertainty principle, is often misunderstood. It's not about being bad at measuring things, or not having sharp enough tools. It's not about the clumsiness of experimenters disturbing what they observe. It's something far deeper than that. It tells us that reality itself refuses to be pinned down. At its most famous, the uncertainty principle says this: you cannot know both the exact position and the exact momentum of a particle at the same time. The more you try to narrow down where something is, the less you know how fast it's moving, and vice versa. The more you define one side of the equation, the more the other dissolves into uncertainty. This isn't optional, it's built into the mathematics of quantum mechanics. Every particle in the universe, from the tiniest electron to the atoms in your body, obeys this rule. And from that one principle, an astonishing conclusion follows. Nothing can ever be completely still. Take a particle in a box. Imagine trying to cool it down. Remove all its energy and let it come to rest. In classical physics, that's no problem. At zero temperature, the particle should stop moving. But in quantum physics, this leads to a contradiction. If the particle stopped completely, we would know both its position, inside the box, unmoving, and its momentum zero. And that, according to Heisenberg, is forbidden. So even when we cool it to the lowest temperature possible, even when all thermal energy has been drained away, the particle still jiggles. It must jiggle. That motion, that irreducible flicker, is not a defect. It is the zero-point energy of the system, a mandatory uncertain, a whisper of motion that cannot be erased. And this doesn't only apply to particles, it applies to fields, the fabric from which all particles emerge. In quantum field theory, the uncertainty principle applies to the field values and their rates of change. That means that the electromagnetic field, even in a vacuum, cannot be perfectly still. The same is true for all fields. They must all fluctuate. They must all contain energy, even in their ground state. These fluctuations are not errors or noise. They are not added after the fact. They are baked into the system, unavoidable consequences of the uncertainty that lives at the heart of quantum reality. It is an unsettling idea. In the macroscopic world we live in, certainty is our anchor. We want to know where things are, how fast they're going, what happens next. And for most of daily life, Newtonian physics gives us what we need. A ball thrown into the air follows a predictable arc. A car moving down a road responds to force and friction. There is order. There is control. But zoom down into the quantum domain, and that order crumbles. Precision gives way to probability. Events are no longer deterministic, but smeared across a landscape of possibility, and even the most basic attributes, where something is, how fast it moves, become uncertain, linked by an invisible thread that refuses to be cut. The uncertainty principle is not just a footnote. It is the reason why zero-point energy cannot be zero. It is the reason why every quantum system has a flaw, a base energy that cannot be lowered, no matter how cold you make it, no matter how carefully you prepare it. This flaw, this irreducible motion, creates ripples that reach far beyond the lab. It gives rise to measurable phenomena. It shifts atomic energy levels, like in the Lamb shift. It pulls metal plates together in the Casimir Effect. It affects the behavior of molecules. It shapes the stability of atoms, and perhaps most mysteriously of all, it may play a role in the expansion of the universe. Because when you sum up the energy of all these quantum fields, all their zero-point vibrations, across the fabric of space itself, you arrive at a staggering number. A number that suggests the vacuum should be flooded with energy, that empty space should be filled to the brim with motion and pressure. And yet, that's not what we observe. Not quite. The vacuum appears to contain some energy, enough to affect the large-scale structure of the cosmos, but not nearly as much as theory predicts. This mismatch, this yawning gap between calculation and reality, remains one of the great unsolved mysteries in physics. A mystery born, at least in part, from the fundamental uncertainty that Heisenberg uncovered. The principle itself is not complex in form. It can be written in a single inequality, yet its consequences are vast. It tells us that we live in a restless universe, not by accident but by law, that every particle, every field, every patch of space, no matter how cold or dark, is infused with motion, that nothing can stop completely, not because something prevents it, but because the very act of stopping would break the rules. This idea touches more than just physics. It hints at something philosophical, even spiritual. That stillness, the thing we associate with peace or perfection, is an illusion. That at the smallest scales, everything is dancing, even if we cannot see it, even if we cannot feel it. And it reminds us that the world is not built from certainty, but from balance, not from fixed outcomes, but from dynamic tensions, between knowledge and mystery, between position and motion, between emptiness and energy. As we continue this journey into the vacuum, into the deep architecture of space itself, the uncertainty principle will follow us like a quiet shadow, because everywhere we go, it will be there, reminding us, nothing can ever be known completely, nothing can ever be made still, and what we call nothing may, in fact, be the most vibrant thing of all. Chapter 5. The Casimir Effect. Energy from nothing. Imagine placing two mirrors face to face, perfectly parallel, with an incredibly small gap between them, just a few nanometers, thinner than a strand of DNA. Between these two surfaces, there is no light, no air, no particles. The space is as empty as science can make it, a vacuum purified of all matter. And yet, within that tiny space, something astonishing happens. The mirrors begin to move. Slowly, gently. They are drawn toward each other, as if by an invisible hand. No charges, no magnets, no strings, just space and a mysterious force. This strange attraction is not science fiction. It is not hypothetical. It is real, measurable. It has been observed in laboratories and confirmed again. It is known as the Casimir Effect, and it is one of the clearest, most direct proofs that even the vacuum, even the emptiest space imaginable, contains energy. To understand how this works, we need to go back to the idea of quantum fluctuations. As we've seen, the vacuum is not truly empty. Even when stripped of all matter and cooled to absolute zero, space still teems with activity. with fields jittering and virtual particles flickering in and out of existence. These fluctuations occur across a wide range of frequencies, from the lowest, longest wavelength to the highest, most energetic ripples. In the open expanse of free space, all these modes are allowed, but when two conducting plates are placed close together, something changes. The gap between them sets a boundary, a limit. Only certain wavelengths of fluctuation can fit between the plates, in the same way that only certain notes can resonate within the body of a guitar. Waves that are too long to fit between the plates are excluded. This creates an imbalance. Outside the plates, all fluctuations are permitted. Inside, only a subset survive. The result is a subtle but measurable difference in pressure. The vacuum fluctuations outside the plates are slightly stronger than those between them, and that difference is enough to nudge the plates inward, to create a force from nothing. This force, though small, is not negligible. In experimental setups with plates separated by less than a micrometer, the Casimir force becomes strong enough to influence nanoscale machinery. In fact, it's something that engineers and designers of tiny systems must take into account. In the world of microelectromechanical systems, MEMS, this vacuum force can cause parts to stick, fail, or move in unexpected ways. The Casimir effect was first predicted in 1948 by Dutch physicist Hendrik Casimir as a theoretical consequence of quantum electrodynamics. It remained a theoretical curiosity for decades until technology advanced far enough to measure such delicate forces. And when the experiments were done, painstakingly with extreme precision, the effect was confirmed. Again and again, space, it seemed, could push. This changed everything. The Casimir effect is not just a technical footnote in physics. It is a window into the hidden energy of the vacuum. It shows, beyond theory, that zero-point energy is not just real. It has consequences. It can exert force. It can influence matter. It can shape the world even when nothing appears to be present. What makes this so remarkable is that the Casimir effect emerges entirely from the quantum structure of space itself. No external fields are applied. No charges or currents are involved. The force arises solely because of the geometry, because of the boundary conditions imposed by the plates. In essence, the plates sculpt the vacuum, reshaping the quantum fluctuations around them, and the vacuum responds. It's as if empty space has preferences, as if it can be stretched, distorted, or altered, not in the way we stretch a rubber band, but in the frequencies and modes of the fields that inhabit it. And this is not limited to metal plates. Similar effects have been predicted and observed in other systems, between atoms, between molecules, even in condensed matter systems. The vacuum, it seems, is malleable, not soft like clay, but dynamic in its own ghostly way. Some physicists have gone further, wondering if the vacuum can be shaped to produce force. Can it also be shaped to produce energy? Could we one day engineer systems that extract usable work from these fluctuations, from the energy of nothing? Could the Casimir effect become more than a lab curiosity? Could it become a power source? Mainstream physics is cautious. Thermodynamics sets hard boundaries. The zero-point energy of the vacuum is not something we can simply plug into a machine and use to boil water or power home. The Casimir effect rearranges energy. It does not create it. And yet, the possibility lingers. There are speculative ideas, theoretical devices, fringe proposals, all attempting to harness vacuum energy. Most are flawed. Some are outright pseudoscience. But the fact remains. The Casimir effect proves that the vacuum is not passive, that it is not empty, that it can push, that it can act. And this raises profound questions. If the vacuum can exert force, what role does it play in the architecture of the universe? Could it help explain dark energy, the mysterious force accelerating cosmic expansion? Could it influence the birth of particles in high-energy environments, like the early universe or the edges of black holes? Could it, in some deep way, be the engine of creation itself? At its heart, The Casimir effect is a reminder, a quiet but powerful signal, that the universe is never truly still. That space, as quiet as it may seem, is alive with possibility. That even in the absence of matter, force can emerge, motion can arise, something can come from nothing. And so these tiny plates, floating in a vacuum chamber, doing their delicate dance, are telling us something big. They are whispering the truth of the vacuum, that it is not a void, but a presence, not a silence, but a... They are revealing a hidden architecture of reality, woven not from matter, but from fields and fluctuations, a structure not built by stars or galaxies, but by the rules of quantum uncertainty playing out in infinite silence. The Casimir effect is not a trick, it is not an illusion, it is the vacuum speaking. And what it says in force, in motion, in undeniable action is simple and stunning. I am not nothing. Chapter 6. Heisenberg's uncertainty principle and the vacuum's motion. By now, one truth has begun to settle like a quiet echo. The vacuum is not empty, and it never sits still. But if we wish to truly understand why, we must return again to the principle that makes all stillness impossible. The strange and elegant logic of Heisenberg's uncertainty, not just applied to particles but to the vacuum itself. In the chapters before, we explored this principle in relation to position and momentum, the twin variables that cannot be simultaneously known with perfect precision. But Heisenberg's insight reaches far deeper. It extends to energy and time, and in doing so, it becomes the heartbeat of the quantum vacuum. The energy-time form of the uncertainty principle tells us this. The more precisely we try to measure the energy of a system, the less precisely we can know how long that energy will last, and vice versa. In short, nature allows for brief, spontaneous appearances of energy so long as they vanish quickly enough. This loophole, tiny and strict as it is, creates an astonishing result: the temporary birth of energy from nowhere. Not infinite, not uncontrolled, but just enough, just long enough. Tiny fluctuations in energy that appear, ripple through space, and dissolve, without violating the laws of physics. These are the quantum fluctuations of the vacuum, made possible not by magic or mistake, but by the same principle that forbids certainty. These fluctuations aren't predictable. They don't form patterns or waves you can track. But statistically they exist. Their consequences build up. They shape the behavior of atoms, the structure of space, even the boundaries of what we call reality. This is why zero-point energy never goes away. Because even in the lowest possible energy state of a quantum system, even when cooled to absolute zero, the uncertainty principle still demands motion. Not optional motion, not residual noise, but built-in, law-bound restless. A system cannot have precisely zero energy because doing so would imply a perfectly known state, a violation of the deepest law quantum physics enforces. And the vacuum, being the lowest energy state of all fields, is governed by this rule. It must fluctuate. It must move. That motion, however, is not like the chaotic tumble of gas molecules or the pulsing of a star. It is quieter, more fundamental. Imagine a calm ocean surface under a sky of infinite silence, but one that never flattens completely. There are always ripples, not from wind, not from life, but from the fabric of the ocean itself. That's the quantum vacuum. That's the consequence of Heisenberg's rule, playing out across every cubic centimeter of space. But what does it mean, really, to say the vacuum is in motion? We don't mean that particles are drifting through it, not in the classical sense. We mean that the very fields that define reality, electromagnetic, strong, nuclear, weak, Higgs, gravitational, are all alive with tiny perpetual undulations. And every point in space is a stage for this. Every inch of emptiness is a battleground of emergence and cancellation, creation and annihilation. Virtual particles, those elusive flickers of existence, rise and fall as part of this restless sea. They don't break rules, because they vanish before they can be caught. Their lives are permitted by the very rule that governs their transience. They are born, not from mass or force, but from uncertainty. And though they last for only the briefest moments, their influence is real, measurable. They tweak the properties of atoms, they push plates together, they may even shape the fate of galaxies. All of this quiet storm within the vacuum, is made necessary by a principle that denies stillness. The vacuum is in motion because it must be, not because of heat, not because of particles, but because stillness in quantum physics is a forbidden state. Think of it this way: if the universe were a song, the vacuum would be the ever-present background note, not heard directly, but vital to the harmony. It is the bass line that never fades, the drone beneath the melody, the rhythm beneath the silence, and like a song, it is shaped by rules, not just aesthetic ones, but mathematical ones. The uncertainty principle is the composer. It dictates what is allowed, what can rise and fall, and how motion must exist, even in the absence of sound. But here in this realm of forced motion, of jittering vacuums and impermanent particles, arises a deeper tension. If every quantum field must fluctuate, and every point in space must carry some minimum amount of energy, then where does all that energy go? How is it accounted for? How does the universe carry so much silent motion without ripping itself apart? When physicists attempt to calculate the total zero-point energy of the vacuum, summing up the contributions from all modes, all frequencies, all fields, they arrive at an answer so absurdly large, it dwarfs every form of energy we know. It's not just big, it's incomprehensible. A value so huge that if real, space itself should explode, galaxies should fly apart, stars should vanish in a blur of expansion. But they don't. Something cancels that energy, or contains it. Some principle we don't yet understand tempers the vacuum's fury, quiets its roar, and leaves behind only a faint whisper, the slow stretching of space known as dark energy. We'll explore that mystery soon, but for now we sit with this, that the vacuum is a sea of required motion, not optional, not excess, but necessary. A result of the universe's refusal to stand still. And we begin to realize something even deeper, that motion is not something added to the universe, it is the universe. That fluctuation, uncertainty and imbalance are not bugs in the system, they are the system. The vacuum moves because the laws of physics say it must. The energy within space itself hums with invisible motion, not because something is disturbing it, but because nature forbids peace without price. What we call nothing is not a blank slate waiting to be filled. It is a theater of laws already at play, an orchestra already in motion, a world of movement, born not from chaos, but from the most disciplined rule in all of quantum physics. Heisenberg's uncertainty principle is not simply a restriction, it is a sculptor, and what it sculpts quietly, relentlessly and everywhere, is a vacuum that can never rest. Chapter 7. Virtual particles, flickers of the quantum sea. Somewhere in the fabric of space, at scales too small to imagine and too fast to measure, particles are born and vanish in a breath shorter than time itself. They do not follow the ordinary rules. They cannot be captured or weighed. They do not travel through space like the particles we know, yet their presence is felt in the structure of atoms, in the motion of planets, in the expansion of the universe itself. These are virtual particles, the strange children of the vacuum, born not from matter or energy in the traditional sense, but from the very uncertainty that defines quantum physics. They are not particles in the classical sense. You cannot hold them in a detector, trace their path, or study their behavior the way you would with an electron or photon. But they are real, not in the way that rocks and rivers are real, but in the way that shadows are real. in the way that a breeze is felt, even when it is unseen. Virtual particles exist for only an instant, permitted by the Heisenberg uncertainty principle, which allows short bursts of energy to appear and disappear as long as they do so quickly enough to avoid violating the conservation laws. They flicker into being, interact briefly with the world, and then vanish back into the vacuum. They are the briefest flicks of existence, so short-lived, so subtle, that their individual presence cannot be measured. And yet, in the aggregate, they reshape the universe. They are the messengers of forces. In quantum field theory, the fundamental interactions between particles, electromagnetism, the strong and weak nuclear forces, are mediated by the exchange of these virtual particles. When two electrons repel each other, we don't imagine them pushing each other directly. Instead, we describe the interaction as the exchange of virtual photons, invisible, momentary flickers of light that appear between them and carry the electromagnetic force. Likewise, the strong force that binds protons and neutrons inside atomic nuclei is mediated by virtual gluons. The weak force, responsible for radioactive decay, is carried by virtual W and Z bosons. All around us, at every moment, space is filled with the buzz of these non-particles, brief interactions that never fully become. They leave behind traces, not in isolation, but in the effects they produce. The Casimir Effect, a result of vacuum fluctuations, themselves a sea of virtual particles. The Lamb shift in hydrogen atoms, caused by the dance of virtual photons with orbiting electrons. Even the magnetic moment of the electron, one of the most precisely measured quantities in all of science, must include the effects of virtual particles to match experiment. In this way, the quantum vacuum is not just a passive emptiness, it is active, responsive, participatory. A stage filled with players that emerge only to vanish, never long enough to bow, never still enough to see, but always present in the outcome. And the term virtual doesn't mean imaginary, it means off-shell, a technical term in quantum field theory that describes entities that don't obey the usual relationship between energy, momentum, and mass. Real particles sit on the shell, a constraint dictated by special relativity. Virtual particles live off the shell, existing for such short durations that these constraints are momentarily lifted. They are allowed to break the usual rules, precisely because the universe keeps strict limits on how long they can break them. It is not anarchy, it is structured exception. Brief freedoms, confined by deeper laws. This is what makes virtual particles so fascinating. They are not merely mathematical tricks, they are not ghosts, they are features of the theory, and the theory works. It predicts things to impossible levels of precision. It allows us to build technologies, lasers, semiconductors, MRI machines, atomic clocks, that depend on interactions shaped by the vacuum. And yet, despite all this, we have never seen a virtual particle directly. We see only what they do. Their presence is always inferred, never observed. They are the hidden hands behind the visible machinery of nature. It is tempting to imagine them as popping in and out of existence in a literal sense, like soap bubbles in air. But this picture, while vivid, is limited. What quantum field theory actually describes is not particles moving through space, but fields interacting. Virtual particles are internal lines in a Feynman diagram, shorthand for deeper mathematical processes. Still, the image remains powerful, because what it tells us is this: even in a vacuum, interactions are happening. Even when all is stripped away, there is still motion, still connection, still consequence. The vacuum is a chessboard in constant play, not with visible pieces, but with invisible rules, whose moves ripple outward into everything we know. And there is another layer to this mystery. If virtual particles are constantly flickering into and out of existence, borrowing energy from the vacuum and returning it just in time, Then what happens when they don't return? Could there be situations where virtual particles become real? The answer, surprisingly, is yes. In certain extreme environments, like the edge of a black hole, or during cosmic inflation in the early universe, virtual particles can be separated before they have time to annihilate. One is swallowed, the other escapes, and in that moment, what was virtual becomes real. This is part of the mechanism behind Hawking radiation, the theoretical process by which black holes can slowly evaporate. Virtual pairs form at the event horizon. One falls in, the other escapes. To an outside observer, it appears as though the black hole is emitting particles. Energy has left the system. Mass decreases, the black hole shrinks. This process suggests that the boundary between the virtual and the real is not absolute. Under the right conditions, the vacuum gives birth. The ephemeral becomes permanent. The flicker becomes flame, and that possibility leads us into breathtaking questions. Could the entire universe, our stars, our galaxies, ourselves, have emerged from a fluctuation in the vacuum? Could a quantum fluctuation, allowed by uncertainty and sculpted by gravity, have sparked the Big Bang? These are not wild guesses. These are real hypotheses in cosmology. Because if virtual particles can be promoted to reality under the right conditions, and if space is never truly empty, then the potential for creation lies embedded in the very structure of nothing. Virtual particles remind us that space is not silent, that even in absence there is activity, that even in stillness there is structure, and that what we call nothing may in fact be the most dynamic environment of all. In the quiet sea of the vacuum, flickers come and go. They do not linger, they leave no footprints, but they change the world with every appearance. They carry force, they shift energy levels, they bend the rules, only to obey deeper ones. And as we listen more closely to the song of the vacuum, we begin to see them not as anomalies, but as messengers, subtle, fleeting, but vital. The flickers of a hidden sea, always in motion, always alive. Chapter 8. Fields, not particles. The real foundation of reality. To truly grasp the mystery of zero-point energy, we must now step back from the familiar terrain of particles, those little marbles we imagine zipping through space, and turn our attention to something deeper, something more fundamental. Because despite what our intuition tells us, despite what textbooks may have once implied, particles are not the true building blocks of reality. Fields are. This may seem like a subtle shift, but it is not. It is a revolution, a redefinition of what matter is, of what space is, of what existence is. Because in quantum physics, the universe is not made of individual objects occupying space. It is made of fields that fill all space. And what we perceive as particles are simply localized excitations, little ripples on top of those fields. Imagine the surface of a vast ocean. To the untrained eye, you might focus on the waves, the frothy crests that rise and fall. But those waves are not separate from the ocean. They are the ocean in motion. In the same way, a photon is not a thing traveling through the electromagnetic field. It is a temporary spike, a ripple of the field itself. This perspective is the heart of quantum field theory, the framework that underlies the standard model of particle physics. According to this theory, there is a field for every fundamental particle, and these fields are present everywhere, always. The electron field, the quark fields, the neutrino fields, the Higgs field. Even in the vast emptiness between galaxies, these fields are still there, undisturbed but alive, jittering ever so slightly with quantum fluctuations. Each time a particle appears, what's really happening is that the corresponding field has momentarily surged. The field is agitated, and a blip, a quantized burst of energy emerges. That burst is what we call a particle, but the field is what's real. The particle is simply its temporary manifestation. So when we speak of zero-point energy, we are speaking of the lowest possible energy state of these fields. And even at their minimum, even when all external excitations have vanished, the fields still retain a trace of motion, a hum, a ripple. That's the zero-point energy. That's the true nature of what we've been calling nothing. This understanding overturns centuries of thinking. Classical physics taught us to see the world as made of little solid things, particles bouncing and colliding, like billiard balls on a table. Even in early quantum mechanics, particles were still treated as point-like objects. But quantum field theory revealed a deeper truth, that particles are not things in space, they are temporary patterns in the fields of space itself. And these fields do not come and go, they do not fade with distance, they do not vanish in a vacuum. They are permanent, ever-present features of reality, a kind of invisible fabric stretched across the entire cosmos. Even more astonishing, these fields interact, they overlap, they interfere. The electromagnetic field talks to the electron field, which talks to the quark fields, which are shaped by the Higgs field, a delicate choreography that produces everything we know, every atom, every molecule, every structure in the universe. And at the base of this dance is the vacuum state, the calm surface of these fields, alive with zero-point motion, not a passive void, but a dynamic equilibrium, a state of energy that never quite rests. And this vacuum is not just a place, it is not a background, it is a physical condition, one that shapes the behavior of every particle, every force, every interaction. It is easy to forget how radical this is. We grow up thinking of space as empty, as nothing, as a neutral canvas on which matter plays out its story. But quantum field theory tells us that space is full of invisible energy, full of structure, full of potential, and that the fields living there are not secondary, they are primary. They do not exist in space. They are even time in this view becomes a parameter through which the fields evolve, but the fields themselves are the substance of reality. This reorientation forces us to ask new questions. If the vacuum is defined by these underlying fields, and if their lowest energy state still contains motion, then how do we define true stillness? Can there be such a thing as a total absence of activity? Or is stillness an illusion, a coarse-grained average that smooths over the constant jitter of the quantum world? And it raises another possibility, that the origin of all particles, all mass, all form, is encoded in the nature of the vacuum, that when the universe was born, it did not begin from nothing, but from a vacuum full of potential, a calm sea of fields, ready to ripple into creation. Indeed, the Higgs field, one of the most celebrated discoveries in modern physics, is itself a vacuum field. It pervades all of space. Its Naso value in the vacuum is what gives mass to particles. Without it, the electron would be massless, atoms wouldn't exist, chemistry wouldn't happen, life would be impossible. And so we return again to this core truth. The vacuum is not empty. The vacuum is not dead. It is a living, structured, energetic medium, a canvas made not of nothing, but of fields, rich with motion, interaction, and memory. When you are surrounded by darkness, you are not in absence, you are immersed in field. When you see nothing, you are looking through the architecture of the quantum world. And when you imagine silence, you are actually listening to a universe whispering with zero-point energy. This understanding reshapes not only physics, but philosophy, because it blurs the line between substance and space, between energy and form. It invites us to think of reality not as a collection of things, but as a network of fluctuations, a sea of invisible continuous motion, from which matter and energy emerge like temporary sculptures carved from waves. Particles will always be the language of measurement, of detection, of experiments, but fields are the true grammar of the cosmos. And zero-point energy, that restless hum, is their ever-present signature. Chapter 9. The fabric of space is never still. If you could somehow silence every atom, cool every particle to the edge of stillness, strip away every photon, every whisper of heat, you might think you've reached the bottom of existence. You might imagine you've arrived at the blank slate, the quiet canvas beneath all things, but even then, you would not find stillness. Because the truth is, space itself cannot sit still. This is not poetry. This is physics. It is the legacy of uncertainty, the echo of fields, the mathematical consequence of the quantum world. The vacuum, that supposed emptiness between particles, between stars, between galaxies, is a seething, restless ocean, a foam that churns even when nothing else remains. The fabric of space is stitched with motion. Not in the way wind rustles leaves or water laps against a shore, but in a deeper, quieter way. A jittering that does not come from outside but from within. A motion that is not caused but required. We call it zero-point motion, the ever-present fluctuations of quantum fields in their lowest possible energy state. It is the hum beneath the silence, the tremble beneath the void, the unceasing rhythm of a universe that never truly pauses. And this motion is not metaphorical, it is real. It has pressure. It has consequences. It affects how particles behave. It alters how atoms bind. It shifts energy levels inside matter. It can be measured, not directly perhaps, but through its fingerprints, left behind in every interaction it touches. Even light, which we often think of as a pristine, perfect wave, is born from this fluctuating fabric. The electromagnetic field, the one that gives rise to light, is alive with zero-point energy. Even in perfect darkness, it ripples. Even in absolute vacuum, it vibrates. The same is true for all fields. For the fields that carry force, for the fields that give particles mass, for the fields that define what we even mean by matter. None of them rest, none of them flatten out to zero. Instead they shimmer, quietly, constantly, with motion that never stops and never slows. This has profound implications. First, it means that space is not neutral. It is not a passive container for things. It is a dynamic player in the story of the universe. It is responsive, flexible, energetic. It can stretch, bend, ripple, twist. In Einstein's general relativity, we learned that space can curve under the influence of mass and energy. In quantum field theory, we learned that space is energy, even before mass enters the seed. Second, it means that there is no such thing as absolute stillness, not at the deepest level. What we experience as calm is a kind of illusion, a surface average, smoothed out by scale. But zoom in far enough, and you'll see it. The eternal twitching of the fields, the flicker of fluctuation, the activity that never ends. Third, it means that the vacuum has structure, not in the sense of walls or edges, but in terms of behavior. The vacuum is not uniform. It responds to boundaries, to conditions, to geometry. The Casimir Effect proves this. Change the shape of space, even in a vacuum, and the vacuum responds. It changes the distribution of its fluctuations. It pushes, it pulls, it exerts force. This suggests that the vacuum is not empty, but sensitive, a medium that can be tuned, shaped, perhaps even engineered, and this opens doors to the future. If the fabric of space is dynamic, if it can be shaped and manipulated, then could we someday harness it? Could we build technologies that tap into the fluctuations, rearrange them, or ride their contours? Could we someday shape the vacuum itself? There are those who dream of such things. Vacuum energy drives, warp bubbles, propulsion systems that interact not with matter, but with the geometry of space itself. Most of these remain firmly in the realm of speculation, but the foundation is real. The vacuum is not silent, the fields are not still, and energy is everywhere. Even more mysterious is the possibility that this vacuum motion may be linked to the expansion of the universe. In cosmology, we observe that space is stretching. Galaxies are flying apart, not because they are moving through space, but because space itself is expanding between them. This expansion is not slowing down, it is speeding up, and we don't know why. We call it dark energy, a placeholder term for something we cannot yet explain. But one idea is that this dark energy might come from the zero-point energy of the vacuum, that the jittering of quantum fields might, on cosmic scales, create a kind of pressure, an outward push that drives galaxies apart. This would mean that the trembling of nothingness is not just local, it is cosmic, that the fabric of space, by refusing to rest, is expanding itself outward, dragging stars with it, reshaping time as it moves. But here lies the paradox. When physicists calculate the expected energy density of the vacuum, the total contribution of all zero-point fluctuations across all fields and frequencies, the answer they get is catastrophically large, larger than what we observe by 120 orders of magnitude. That's a 1 followed by 120 zeros, the largest known discrepancy between theory and observation in all of physics. This is called the vacuum catastrophe. It means that something is missing in our understanding, that either we are overcounting, or something cancels the energy we expect, or that a deeper theory still undiscovered hides beneath what we now know. But one thing is certain, the motion is real. The vacuum is not blank. It is a field of overlapping vibrations, in perfect balance, each one jittering just enough to honor the uncertainty principle, none able to vanish completely. And that balance, that gentle eternal struggle, is the reason why space itself is never still. You are sitting in it right now, between you and the screen, between every breath, between every atom. Motion, endless, invisible, unceasing, not because something disturbs it, but because the rules of existence require it. Chapter 10. The zero-point field and the universe's energy budget. If the vacuum teems with energy, if every cubic centimeter of empty space hums with fluctuations that never cease, then a question begins to echo louder than all the others. How much energy is there really and nothing? It sounds like a contradiction, a trick of language. But this is not a word game. It is one of the most serious, unresolved problems in modern physics. Because if space itself contains energy, and all of quantum field theory says it does, then that energy must be accounted for. It must appear in the equations that govern the expansion of the universe, the behavior of galaxies, the fate of everything. And yet, it doesn't. Or at least, not in the way we expect. Let's start at the smallest scale. When physicists calculate the zero-point energy of a single mode of a quantum field, say a simple electromagnetic wave trapped between 2 points, the math is clean. The energy isn't zero. It's a finite, non-zero value, proportional to the frequency of the wave. But space doesn't contain just one wave. It contains all possible waves, all frequencies, all modes of vibration, all the way up to the highest energies that nature allows, or in theory infinitely. So when we add up the contributions of all these modes, the zero-point energy from every possible frequency of every field at every point in space, the result we get is infinite. The vacuum, according to this math, contains an infinite amount of energy. But infinity is a red flag. In physics, infinity usually means something has gone wrong, or that our theory has reached beyond its valid limits. So instead of accepting that absurd answer, we impose a cutoff, a limit, to how high those frequencies can go. Often we set that cutoff at the Planck scale, the point where our understanding of space-time breaks down and quantum gravity must take over. With that cutoff in place, the answer becomes finite, still enormous, but no longer infinite. And here comes the shock. Even with this cutoff, the predicted vacuum energy is still 20 orders of magnitude greater than the energy density we actually observe in the universe. Let that sink in. A number not 10 times too large, not 1,000, but a 1, followed by 120 zeros. That's like predicting the weight of a coin and finding your theory overshoots by the mass of the entire visible universe. And then, this is the cosmological constant problem. And it is the most dramatic mismatch between theory and observation in the history of science. Because according to general relativity, energy curves space-time, and so the vacuum energy, if it really were that enormous, would curve space-time so violently that the universe would have exploded or collapsed long ago. But it didn't. Instead, what we observe is far more. The universe is expanding, yes, and even accelerating in that expansion, but the force driving it is gentle, quiet, persistent, not the wild violence of a vacuum overflowing with energy, but the slow push of something very small, very constant, and very mysterious. We call it dark energy, and it makes up about 70% of the total energy budget of the universe. Not stars, not black holes, not galaxies, but a smooth, invisible pressure that pervades all of space, acting not locally, like gravity, but globally, across cosmic scales. And some believe this dark energy is the faint echo of the zero-point field, that somehow, amid all the violent fluctuations predicted by quantum theory, most of that energy cancels out, perhaps through symmetry, or some hidden mechanism we've yet to uncover, leaving behind only a whisper, a residue, a remainder that expands the universe without tearing it apart. But if such a mechanism exists, we do not know what it is. We have no equation to balance the ledger, no symmetry to cancel the excess. We simply live with the mismatch, knowing that the vacuum should be screaming, but somehow is whispering instead. And still, the whisper changes everything. It means that even the vastness of the cosmos is shaped by the smallest things imaginable, that the push behind galaxies flying apart may come not from mass, not from force, but from the ever-present tremble of invisible fields. It also means that energy is everywhere, not in concentrated lumps, like stars, but spread evenly across all of existence. This energy does not clump. It does not curve space the way matter does. It does not interact directly with light or atoms, but it stretches space. It expands it. It accelerates the distances between all things. This is the strange nature of vacuum energy. Unlike mass, which attracts, vacuum energy exerts negative pressure. It pulls outward, not inward. It drives expansion, not collapse. And the more space you have, the more vacuum energy there is, not because it dilutes, but because the energy per volume remains constant. As the universe grows, so does the total amount of vacuum energy, not because anything is being added, but because more space means more vacuum. This is a hard idea to grasp. It defies our intuition about conservation, about limits, about what energy even means. But this is the nature of the zero-point field. It is not a fuel, it is not a flow, it is a property of space itself. And so the universe expands, not into something, but into more of itself, into more vacuum, into more energy, into more nothing, which is not truly nothing at all. If the zero-point field is responsible for this, if it truly drives the expansion of the universe, then it is not a background character in the cosmic story. It is a lead, a force that sculpts time, shapes galaxies, determines the fate of all things, and yet we are still in the dark. We do not know why the vacuum energy does not explode. We do not know why it is not zero. We do not know what balances its scales, what tames its fury, what hides its full strength. We only know that it is there, quiet, constant, everywhere, a pressure without contact, a force without form, an energy that emerges not from matter, but from the restless stillness of the fields that live in space itself. In the end, the zero-point field is not just a curiosity. It is the unseen majority, the dominant player in the universe's budget, the proof that even when all things are stripped away, space still has a cost, and that cost is energy. The energy of being, the energy of motion, the energy of nothing that turns out to be everything. Chapter 11. The Vacuum Catastrophe. There are errors in science, small ones, correctable ones, the kind that sharpen our theories and refine our instruments. And then there are errors so large, so bewildering, that they stop us in our tracks. They don't just signal a mistake, they tell us something deeper is broken, something fundamental is missing. The vacuum catastrophe is one of those errors. It is not a myth. It is not a misunderstanding. It is a real, calculated, quantified mismatch between what quantum theory says should happen and what actually does. And it is, by all accounts, the most staggering failure in the history of theoretical physics. To understand this catastrophe, we must return to the idea of the zero-point field, the baseline energy of every quantum field that permeates the vacuum. Each field, the electromagnetic field, the Higgs field, the gluon field, and countless others, contributes its own tremble, its own quantum jitter to the vacuum's energy. These fluctuations exist at every point in space, and they span every possible frequency, from the slowest undulation to the sharpest, highest energy spike. And while each contribution may be tiny, their number is vast, infinite, in fact, unless we impose a limit. So to keep things manageable, physicists cut off the calculations at the Planck scale, the energy level beyond which quantum gravity would presumably dominate, and where our current theories stop being reliable. Even with that cutoff, the predicted energy density of the vacuum, the sum total of all these quantum fluctuations, is incomprehensibly large. Not metaphorically large, not merely surprising, but large in a way that shatters logic. Specifically, it's 10 trillion times greater than the observed value. That's a 1 with 120 zeros. The largest known discrepancy between theory and measurement. A difference not of precision, but of cosmic proportion. To put it in perspective, imagine you predict that something should weigh as much as the entire Earth, and then you measure it, and it weighs less than a grain of dust. That's the scale of the failure we're talking about. This is the vacuum catastrophe. The term was coined by physicist Steven Weinberg, who helped pioneer many of the theories we still use today, and it remains a scar on the otherwise gleaming surface of quantum field theory. A problem that no one has solved, not because no one has tried, but because it points to a tension between two great frameworks of modern physics. On one side, we have quantum field theory, which describes particles and their interactions with astonishing precision. On the other, we have general relativity, which describes how energy and mass curve spacetime, governing the expansion of the universe. Each works beautifully in its own domain. But when we try to connect them, when we let quantum field theory predict the energy of the vacuum, and let general relativity interpret that energy as a curvature of spacetime, everything falls apart. According to quantum theory, the vacuum should be catastrophically energetic. According to relativity, that energy should cause the universe to expand so violently that galaxies could not form, stars could not survive. We would not be here, but we are here. The expansion is real, but gentle. Space stretches, but it does not explode. The catastrophe is in the math, not in the sky, and so we are left with a puzzle. Where did all that predicted energy go? Did it somehow cancel itself out? Did positive and negative contributions balance perfectly, leaving only the faint remainder we call dark energy? Or is there a hidden mechanism, some symmetry, some law, that forces the vacuum energy to nearly vanish? No one knows. Many theories have been proposed. Supersymmetry, for example, offers a tempting solution. By pairing each particle with a partner of opposite spin, the contributions to vacuum energy could, in theory, cancel each other out. But we have yet to find experimental proof that supersymmetry is real. Other ideas involve anthropic reasoning. The controversial notion that perhaps the vacuum energy appears small in our universe because a larger value would prevent life from forming. And we only exist in a universe where that didn't happen. In this view, there may be countless other universes with different values of vacuum energy, but we happen to be in one where things worked out. That's the multiverse explanation, and while intriguing, it remains untestable. Still others believe that the resolution lies in a new theory of quantum gravity, one that we do not yet possess, a theory that unites the quantum and the cosmic, that respects the truths of both quantum field theory and general relativity, but avoids their contradiction. Perhaps such a theory will reveal that vacuum energy is not what we think it is, that it emerges not from the fields we know but from deeper structures or deeper emptiness than we have yet imagined. Until then, we live with the catastrophe. We build our theory, we make our measurements, we design our telescopes, measure the cosmic microwave background, map the expansion of the universe, and all the while we know quietly, uncomfortably, that the numbers do not line up, that somewhere beneath our understanding, a fundamental mistake waits to be uncovered. The vacuum catastrophe is not just an error in prediction, it is a crack in the foundation, a hint that we have seen only the surface of things, and that beneath that surface, something else is moving, something we do not yet understand. And yet, in a way, this failure is not defeat, it is a signal, a signpost. Because in physics, the biggest breakthroughs often come from the biggest problem. And this mismatch between the theory of everything and the expansion of everything may be the problem that leads us to the next revolution. Until then, we continue to look into the silence. We listen to the hum of the vacuum. We follow the tremble of the zero-point field. And we carry in the heart of our science a mystery too loud to ignore. Why does the vacuum not explode? Chapter 12. Can we harness zero-point energy? We live in a world that runs on energy. From the heat of the sun to the burning of coal, from the flow of rivers to the spinning of turbines, we harvest motion from nature and turn it into power. But always there are limits. Fuel runs out, heat dissipates, engines lose efficiency. And as we push deeper into the future, building faster machines, larger cities and more complex systems, one question begins to loom. Could we one day tap into the energy of the vacuum itself? It sounds like science fiction, an endless reservoir of power drawn not from the Earth, but from the very structure of space. A well that never dries, a source that requires no sun, no wind, no fire, just space and the invisible motion within it. This idea, harnessing zero-point energy, has haunted the imaginations of physicists, futurists, and inventors for decades. It promises everything: infinite energy, silent propulsion, the end of scarcity. But as with many promises whispered by the universe, the reality is more complex and far more mysterious. First, the facts. Zero-point energy is real. It is not speculative. It has been observed indirectly through phenomena like the Casimir Effect and the Lamb shift. The vacuum has energy. The fields fluctuate. This is not disputed. But the challenge lies not in proving that the energy exists. The challenge lies in extracting it. The energy of the vacuum is not like the energy of a spinning wheel or a moving river. It is not available in a concentrated form, waiting to be tapped. It is a baseline, the lowest energy state a quantum field can occupy. It is not above zero, it is the zero, and by definition, you cannot go lower than the ground floor. In thermodynamics, this has profound consequence. For an engine to do work, to produce usable energy, there must be a difference in energy, a gradient, a fall from high to low, like water turning a wheel as it descends. But if zero-point energy is already the lowest state, where is the slope? Where is the drop? The answer at first glance is simple. There is none. which is why most mainstream physicists are skeptical of schemes to extract usable work from the vacuum. The laws of thermodynamics, they argue, forbid it. You cannot build a machine that runs on zero-point energy for the same reason you cannot build a machine that runs on stillness. And yet, the Casimir effect complicates the picture. As we've seen, when two plates are placed close together in a vacuum, the energy density between them becomes slightly lower than in the space outside. The result is a force, a pressure that pushes the plates together. This difference, small as it is, creates motion. It does work. It is energy. So does this mean we can extract that energy? Not exactly, because to reset the plates, to pull them apart and start the cycle again, requires just as much energy as the force provides. You gain nothing. You cannot build a perpetual engine. The system is conservative. It obeys the rules. Still, there are whispers, experimental anomalies, speculative papers, edge-of-the-map ideas. Some propose using metamaterials, structures engineered at the nanoscale, to manipulate vacuum fluctuations in ways nature never intended. Others imagine harnessing the Casimir force in creative geometries, or exploiting the dynamics of moving boundaries to create unbalanced interactions. There are theoretical models, complex, controversial, that suggest under very specific conditions, in highly non-equilibrium systems, it might be possible to convert some of the vacuum energy into useful work. Not a torrent, not infinite power, but a trickle, enough, perhaps, to change what's possible in deep space, or in isolated systems where no other source of energy is available. One of the most famous speculative designs is the dynamic Casimir effect, in which a mirror moves at relativistic speeds through a vacuum, creating photons out of the shifting boundary conditions. This is not science fiction. It has been demonstrated at microwave frequencies, in laboratory conditions. The photons are real. The energy emerges. The vacuum responds. But again, there is a cost. Moving the mirror at such speeds requires input. The energy you get out is not free. The balance holds. Still, the fact that the vacuum can be stimulated, shaped, or stirred into giving up energy even temporarily is profound. It suggests that the zero-point field is not a locked vault, but a dynamic system, one that can interact, one that can respond. And if that's true, then perhaps the dream is not entirely dead. In science fiction, the idea of vacuum energy appears often as warp drives, as zero-point modules, as the silent hum beneath impossible machines. These stories are not grounded in working physics, but they are not baseless fantasies either. They are expressions of a real possibility that the greatest energy source in the universe might be the one we've been swimming in all along. But if we are ever to reach it, truly reach it, we will need more than clever engineering. We will need a deeper theory, a better understanding of how the quantum vacuum interacts with space-time, with information, with entropy. We may need quantum gravity, a new framework that unifies what we know with what we still cannot grasp. Until then, the vacuum remains a mystery, a locked room filled with movement, a silence that vibrates, a sea whose surface we can see but whose depths we have not yet plumbed. Can we harness zero-point energy? Not yet. Can we dream of it? Yet. And maybe that dream, grounded in the strange, undeniable reality of the quantum vacuum, is what will lead us one day to the technologies we can't yet imagine, a way to turn nothing into something, to power motion from silence, to reshape what energy even means. For now, we wait, we watch, we listen to the hum. And we remember, the vacuum is not still, it is not empty, and it is not powerless. Chapter 13. The Myth of Free Energy Machines. Whenever a scientific idea captures the imagination, it draws not only curiosity, but also fantasy, and few concepts have sparked more of both than zero-point energy. The thought that empty space could contain limitless energy, invisible, everywhere, untapped, has ignited visions of a world without scarcity, a world where machines run forever, a world without wires, power plants or combustion. And from those visions a persistent myth has grown, the myth of the free energy machine. It has appeared in patents and prototypes, in internet forums and YouTube videos, in whispered claims and bold declaration devices, said to draw power from the vacuum, to spin endlessly, to produce more energy than they consume. They go by many names: over-unity generators, vacuum extractors, zero-point engines. Some claim to run forever. Others promise to solve the energy crisis, eliminate fossil fuels, and unlock a new era of abundance. But behind these bold claims lies a hard truth, one the universe has made very clear. There is no such thing as free energy. Not because scientists are close-minded, not because governments are hiding the technology, but because nature, in all its beauty and complexity, does not permit it. This is the rule of conservation of energy, one of the most tested and trusted laws in physics. It says that energy cannot be created or destroyed, only transformed. You cannot get more out than you put in. There are no exceptions, no loopholes. Every system must balance. It is also the principle behind thermodynamics, which tells us that you cannot build a machine that runs forever without input, because all machines lose energy through heat, through friction, through inefficiency. Even the most perfect system will eventually run down. Entropy guarantees it. So when someone claims to have built a device that produces more energy than it consumes, a machine that spins forever, that powers itself from nothing, they are not challenging mainstream science. They are challenging the structure of physical law. And yet, the myth persists, partly because it is seductive. The idea of a machine that powers itself, that gives something for nothing, is emotionally irresistible. It speaks to our deepest hopes, for freedom, for control, for mastery over nature. It promises an end to struggle, an escape from limits. And in a world of rising costs and shrinking resources, who wouldn't want to believe? But belief is not evidence, and science is not built on desire. Over the decades, countless free energy devices have been proposed. Some are clever misunderstandings, others are genuine attempts by inventors who believe they've found a hidden truth. A few are outright scams, designed to extract money or fame from the unsuspecting. None have passed rigorous scientific scrutiny. None have produced verifiable, repeatable results under controlled conditions. None have demonstrated energy extraction beyond known sources. And none have overturned the laws of thermodynamics. That includes those claiming to harness zero-point energy, because while the vacuum is indeed full of motion, and while the fields do indeed fluctuate, that energy cannot be freely extracted. It is not like a battery waiting to be discharged. It is the ground state, the bottom floor, and without a difference in energy, without a flow from high to low, no usable work can be done. Even the Casimir effect, often cited by enthusiasts, does not provide free energy. Yes, it produces a force. Yes, that force is measurable, but to repeat the effect, to cycle the plates, to harvest the energy, requires input. The system is balanced. The books are closed. Some argue that vacuum energy is vast, that if we could just find the right frequency, the right material, the right resonance, we could unlock the flow. But physics says otherwise. It says the vacuum is already in its lowest state. There is no hidden valve, no secret force. Others appeal to misunderstood phenomena, tapping into misunderstood versions of Tesla's work, or invoking fringe interpretations of quantum theory, or layering speculative math onto misunderstood experiments. But these too fall short. They confuse the poetic with the precise. They substitute mystery for mechanism. And then, of course, there are the conspiracy theories that governments have the technology but suppress it, that corporations bury inventions to protect profits, that secret labs have cracked the code but keep it hidden. These stories, while compelling, have never been supported by evidence. They flourish in the absence of understanding, not in the presence of proof. In reality, the scientific community would celebrate such a breakthrough. The discovery of a way to extract usable energy from the quantum vacuum in a way that does not violate thermodynamics would revolutionize everything. It would be awarded, published, peer-reviewed, tested, and built upon. Careers would be made. Nobels would be awarded. The world would change. But that day has not come. What has come, instead, is a better understanding of the vacuum, not as a fuel source, but as a fundamental structure, not as a free lunch, but as a tightly governed system, a place where energy exists, yes, but in forms that are balanced, conserved, and bound by the deepest rules we know. That doesn't mean we should stop dreaming, but it means we must dream with discipline. We must distinguish between what is unknown and what is impossible, between what is untested and what is disproven. Because the myth of free energy can do harm. It can waste time. It can mislead. It can drain resources from real innovations, from technologies that obey the laws of physics, but still promise profound change. Solar, wind, fusion, storage, efficiency. These are not fantasies. They are hard problems, but they are possible ones, and they hold the key to the future we seek. So let us not be distracted by impossible promises. Let us instead be guided by the real miracle, that the vacuum itself, though invisible and silent, is alive with motion, that even the emptiest space is full, that the universe gives us not a shortcut, but a mystery, one we must approach, not with wishful thinking, but with courage, clarity, and care. Because truth is not free, it is earned. And energy, like all things in this universe, has a cost. Chapter 14. The link to dark energy. Some forces shout, gravity pulls, electromagnetism sparks, nuclear forces bind and burst. But not all forces are loud. Some are quiet, so quiet they were almost missed. Yet their silence shapes everything. One such force is dark energy, a presence that does not collide, does not radiate, does not glow, but stretches the fabric of space itself. And in the growing mystery of the quantum vacuum, a question rises like a whisper that refuses to go away. Could zero-point energy be the source of dark energy? To answer that, we must first understand what dark energy is, or rather what we know of it. Because in truth, we know very little. In 1998, astronomers made a discovery that shook the foundations of cosmology. They were studying distant supernovae, explosions that serve as cosmic mileposts, expecting to find that the expansion of the universe was slowing down due to gravity. But what they found was the opposite. The universe wasn't just expanding, it was accelerating. Galaxies weren't being pulled back together, they were drifting apart faster and faster. Space wasn't coasting, it was pushing outward, as though something everywhere was applying pressure to the very structure of the cosmos. This force wasn't linked to any known particle. It didn't behave like matter. It didn't act like light. It didn't cluster or curve or concentrate. It was smooth, uniform, persistent, and so, lacking a better explanation, scientists called it what it appeared to be: dark energy. We don't know what it is, but we know how much of it there is. Roughly 70% of the total energy content of the universe is dark energy. Not stars, not dust, not even dark matter, but a smooth, invisible pressure woven into space itself. And here's where the link to zero-point energy becomes impossible to ignore. Because the vacuum is not empty. It is filled with quantum fields, all trembling with zero-point motion. It has energy. It has pressure. It exists everywhere, and its effects, though subtle, are uniform and persistent. That sounds an awful lot like dark energy. In fact, Einstein himself once imagined that the vacuum might have a kind of energy, a cosmological constant, a term he added to his equations to balance the pull of gravity and keep the universe static. He later called it his greatest blunder, after it was discovered the universe was expanding. But perhaps it wasn't a blunder at all, because the cosmological constant, a smooth, unchanging energy density in space, fits what we now observe. It matches the effect of dark energy almost perfectly. The expansion it causes is steady. Its presence is everywhere. It does not dilute as the universe grows. It is space, acting on itself. And so, physicists began to wonder, could the zero-point energy of quantum fields be the cosmological constant? Could the energy of the vacuum, the restless, irreducible tremble of nothing, be pushing the universe apart? Mathematically, it makes sense. The vacuum has energy. That energy creates pressure. And in general relativity, pressure curves space-time. In this case, it uncurves it, driving expansion, not attraction. But then comes the problem. The same catastrophe we've already seen. The amount of vacuum energy predicted by quantum field theory is enormous. Many orders of magnitude greater than the dark energy we actually measure. Once again, the theory overshoots reality by 100. So if zero-point energy is dark energy, we must explain why it appears so quiet. Is there a perfect cancellation happening? Are positive and negative contributions from different fields balancing each other out, leaving only a tiny residue? Or is there a deeper principle at work? A symmetry, a constraint, a law we haven't yet discovered, that suppresses the vacuum energy to the faint murmur we observe? No one knows. Some theories suggest that the vacuum energy does contribute to dark energy, but that only a small portion survives, the rest neutralized by forces or fields beyond the standard model. Others propose that dark energy is not vacuum energy at all, but the effect of some new exotic field, a quintessence field evolving slowly over cosmic time. And still others imagine that what we call dark energy isn't even energy in the traditional sense, but a sign that our understanding of gravity is incomplete, that perhaps space-time behaves differently on vast scales than we think. But regardless of which theory is right, if any are, the resemblance remains. Vacuum energy acts like dark energy, its properties match. Its presence is universal, its pressure is negative, its influence is everywhere. It is not proof, but it is a compelling hint that the mystery of cosmic acceleration and the mystery of the trembling vacuum may in fact be the same. And if they are, then something incredible follows. It means that nothing, literal physical, nothing may be responsible for the largest force in the cosmos. That the greatest actor on the cosmic stage is not a star, not a black hole, not even dark matter, but the invisible motion of fields in the vacuum. It means that space expands not because of what it contains, but because of what it is. Not static, not dead, but alive. And not just alive, but dominant. We live in a vacuum-dominated universe, a cosmos where the most powerful force is not gravity, not electromagnetism, not the nuclear forces, but the silent, continuous push of the vacuum itself. That's the link. That's the whisper. That's the story the universe may be trying to tell us, that the emptiness we once feared is not empty at all, that the void is not cold but burning with silent motion, that what we called nothing is what holds the everything together. And Chapter 15. What Einstein thought about the vacuum. When we speak of the vacuum today, the quantum fields, the zero-point energy, the restless motion beneath stillness, we do so with the benefit of hindsight, of theory, of decades of precision experiments. But long before vacuum fluctuations and the Casimir effect, before dark energy and quantum field theory, one man stood at the edge of an earlier mystery. Albert Einstein. To understand the vacuum through Einstein's eyes is to return to a different cosmos, one not filled with invisible jittering fields, but with smooth geometric order. A universe where gravity wasn't a force pulling through space, but a bending of space itself. Einstein's theory of general relativity, published in 1915, revolutionized our understanding of space and time. In his view, mass and energy curve the fabric of space-time, and objects follow those curves. There is no force of gravity, there is only the shape of the stage. And yet in the equations that describe how matter and energy affect curvature, Einstein faced a strange freedom. A mathematical detail, a constant that could be added to both sides of his famous field equations without breaking the logic. This term had no clear physical origin at the time, but it had consequences. Einstein called it the cosmological constant. He introduced it not because of quantum theory, which barely existed in 1917, but because of something more philosophical. He believed the universe should be static, eternal, unchanging on the largest scales. But his equations without that constant predicted a dynamic universe, one that either expands or contracts. So he added the term, a kind of pressure built into the vacuum itself, to counteract gravity and hold the universe steady. For a time it seemed elegant. Space held together by its own subtle resistance to collapse. A kind of tension in the fabric of the cosmos. But then in 1929, Edwin Hubble made a discovery that changed everything. The universe was expanding. Galaxies were receding from one another. Space was stretching. Einstein's static model was wrong, and so he retracted the term. He called the cosmological constant his greatest blunder, a correction born from philosophy, not physics. But history would turn the tables once again. Decades later, when astronomers observed that the expansion of the universe was accelerating, the cosmological constant was reborn. Suddenly, the very term Einstein had abandoned was the perfect fit for the data. A pressure in the vacuum, a smooth, persistent energy driving the expansion of space. Was it a mistake, or was it a prophecy? Einstein, of course, did not have quantum field theory. He did not know about zero-point energy or vacuum fluctuations. But he understood something that remains central even now, that space is not nothing, that the vacuum is not an empty backdrop, but a dynamic entity, a player in the cosmic game. In his earlier work, Einstein had wrestled with the idea of the ether, not the old 19th century substance that filled space and carried light waves, but a more modern concept, that space itself could have properties, that it could curve, bend, evolve, hold energy. In 1920 he gave a lecture in which he said how, according to the general theory of relativity, space is endowed with physical qualities. In this sense, therefore, there exists an ether. He wasn't resurrecting the old ether. He was pointing to something deeper, a realization that space isn't an empty stage, but a physical medium with structure and behavior. In today's language, we might say, space is filled with fields. Those fields fluctuate, and those fluctuations create energy. Einstein didn't know the equations of quantum vacuum energy, but he gave us the geometric canvas on which those equations now play out. And his cosmological constant, once dismissed, now serves as the simplest explanation for dark energy, the pressure of space upon itself. It's a strange twist of fate. The constant Einstein added to keep the universe still now explains why it won't stop expanding. The term he regretted may yet prove to be the most important idea he ever wrote down. But Einstein's relationship with the vacuum wasn't just mathematical, it was philosophical. He struggled with the idea of randomness, of incompleteness, of the strange probabilistic rules emerging in the new quantum theories. He famously said, "God does not play dice with the universe." To Einstein, the idea that the vacuum could fluctuate, that particles could pop in and out of existence without cause, felt wrong, incomplete, not yet finished. He believed in a deeper order, a hidden layer beneath the uncertainty, a theory that would restore causality, completeness, and predictability to the fabric of space. In this, he may have been both right and wrong. Right, in the sense that our understanding is still incomplete, that quantum mechanics and general relativity remain unmerged, that vacuum energy, with all its contradictions, remains a mystery unsolved. Wrong, in that randomness, it seems, is woven into reality, that the vacuum does jitter, that particles do flicker into being, that the universe is built not from perfect certainty, but from balanced unpredictability. And yet Einstein's legacy lives on in every equation we use to describe the vacuum. His geometry shapes how we understand space. His constant anchors are models of cosmic expansion. His resistance to accepting the incomplete has fueled generations of physicists to search further, deeper, harder. So what did Einstein think about the vacuum? He thought it mattered. He thought it was physical. He thought it had weight and shape and influence. And in doing so, he paved the way for a universe where nothing is never really nothing, but the place where everything begins. Chapter 16. Zero-point energy and the structure of the atom. For all the vastness of the cosmos, for all the galaxies, the stars, the endless black between them, the most extraordinary complexity lies not out there, but within. Inside the atom, within the invisible, the minute, the immeasurably small. And it is here, in the hidden scaffolding of matter, that the vacuum whispers its influence most intimately. Because atoms, like space, are never truly still. To understand how zero-point energy shapes the very structure of atoms is to realize just how deeply the vacuum is woven into the fabric of matter, not as something distant, not as a cosmic background, but as a presence that lives inside every moment of physical existence. Let us begin with the simplest atom of all, hydrogen. One proton, one electron. It is the building block of the universe, forged in the early moments after the Big Bang, and the most abundant element in existence. And yet even this humble atom is ruled by laws that defy classical logic. Classically, you might imagine the electron as a tiny planet orbiting the proton, drawn in by electrostatic force, kept from collapse by angular momentum. But that picture falls apart in the quantum world. If the electron were truly orbiting like a planet, it would be accelerating, and an accelerating charge emits radiation. It would lose energy, spiral inward, and crash into the nucleus. The atom would collapse in a fraction of a second. But that doesn't happen. Atoms are stable. They persist. Electrons do not spiral inward. They remain suspended, bound, held in place by something stranger than classical motion, by quantum probability. The electron does not orbit, it exists in a cloud, a fuzzy, probabilistic region around the nucleus, and that cloud is shaped by quantized energy levels, discrete steps that the electron can occupy but never linger between. Even in the lowest energy state, the so-called ground state, the electron does not come to rest. It cannot, because if it did, we would know its position at the nucleus and its momentum, zero, with perfect accuracy, a direct violation of the uncertainty principle. Instead, the electron remains in motion, its energy locked above zero by the rules of quantum mechanics. This residual, irreducible motion is the atomic signature of zero-point energy. The same principle that keeps the vacuum alive with fluctuations also keeps atoms from collapsing. This is not an abstract idea. It is observable. Consider the Lamb shift, a small, subtle difference in energy levels within hydrogen. discovered in the 1940s. According to simple theory, two specific quantum states should have the same energy, but they don't. One is slightly elevated, shifted by a whisper-thin margin. That shift arises from the interaction between the electron and the vacuum. Specifically, from the vacuum fluctuations of the electromagnetic field. The zero-point energy of the vacuum perturbs the electron's orbit, nudging it ever so slightly, changing the behavior of the atom itself, and we can measure that change. A phantom effect, left by invisible motion, made real in the architecture of matter. And this is just one example. Zero-point energy plays a role in van der Waals forces, the subtle attractions between neutral atoms and molecules. It helps explain the weak stickiness of noble gases, the cohesion of molecular structures, the behavior of liquids and biological systems. It influences bonding, reactivity and vibration, the ways atoms move and connect. In quantum chemistry, zero-point motion affects the ground state of molecular systems, influencing bond lengths and molecular shapes. It's even essential in understanding the difference between hydrogen and its isotope deuterium, a tiny change in mass that leads to measurable differences in chemical behavior, due in part to the shift in zero-point energy. And it goes deeper still. In solid-state physics, zero-point energy explains why helium, the second lightest element, remains a liquid even near absolute zero. Its atoms, too light and too jittery, never settle into a crystalline structure. The vacuum won't let them. Even in biological systems, in protein folding and enzyme reactions, the residual motion at the atomic level, guided by quantum effects, influences the shapes and actions of life itself. In every cell, in every molecule, zero-point motion plays its part. We tend to think of atoms as self-contained protons, neutrons, electrons, spinning in isolation, but in truth, they are open systems, immersed in the vacuum, shaped not just by internal forces, but by the restless energy that surrounds them always. The zero-point field does not merely exist in the emptiness between matter. It penetrates matter. It defines matter. It sets the baseline for how particles behave, how atoms bind, how structures hold. And if that baseline were different, if the vacuum were more still or more violent, chemistry would not function, molecules would not form, stars would not burn, life would not emerge. The very fabric of reality depends on the vacuum's gentle but inescapable whisper. In this way, the vacuum is not absence. It is architecture, a silent engineer, shaping the scaffolding of all things. It determines not just how space behaves, but how matter lives, not just how stars evolve, but how atoms breathe. And so when you touch anything, a table, a book, your own skin, you are touching something that exists, not in isolation, but in conversation with the vacuum, something stabilized by a motion you cannot feel, but that never, ever stops. Every atom is a dance, every bond is a compromise between stillness and motion. And at the heart of that motion is zero-point energy, the ghost in the structure of all things. Chapter 17. The Role of the Higgs Field. There is a question so fundamental, so childlike in its simplicity, that it often goes unasked. Not because it lacks importance, but because we take its answer for granted. Why do things have mass? Why does your body resist acceleration when you push it? Why does Earth have weight? Why does a proton feel heavy, while a photon glides effortlessly through space? Mass, the stubborn, tangible quality that gives substance to the world, is not just there. It is not self-evident. It must come from somewhere, and the story of where it comes from leads us into one of the deepest layers of the quantum vacuum, the Higgs field. The Higgs field is not like a planet, or a particle, or a wave. It is not something you can touch or see. It is a field, an invisible presence that fills all of space, everywhere, always. It is part of the fabric of the universe itself, stitched into the quantum vacuum just like the electromagnetic field or the strong nuclear force. But unlike those other fields, the Higgs field does something extraordinary. It gives particles mass. Here's how. Imagine a room filled with fog. Now picture someone moving through that room. Some people move easily, barely disturbed. Others wade through the mist, slowed and tangled. The fog resists them differently. The Higgs field acts like that fog. Not literally, but metaphorically. It interacts with particles as they move through it. And depending on the strength of that interaction, different particles acquire different masses. Photons, for instance, are immune. They pass through the Higgs field untouched. That's why they are massless, why light moves at the cosmic speed limit. But other particles, like W and Z bosons, interact strongly with the Higgs field, and because of that, they gain mass. They slow down. They become heavy. This interaction is not optional. It is built in. Particles are defined not just by their charge or spin, but by how they talk to the Higgs field. It is part of their identity, woven into the very mathematics of their existence. And where there is a field, there must be a particle. The Higgs boson discovered in 2012 at CERN is the visible ripple of that invisible field. It is not the field itself, but the messenger, the echo, the signature that proves the field is real. This discovery was monumental, not because of the particle alone, but because it confirmed the existence of the field, a field that permeates the vacuum, silently but powerfully reshaping the behavior of everything with mass. But why does this matter in our journey through zero-point energy? Because the Higgs field is not just in the vacuum, it is part of what defines the vacuum. It contributes to the vacuum's energy, its structure, its behavior, and unlike most fields, the Higgs has a non-zero vacuum expectation value, meaning it doesn't average to zero even in its ground state. In other words, the vacuum is not symmetric. It is biased, skewed, tilted in the direction of mass. This tilt is what allows symmetry to break, a phenomenon called spontaneous symmetry breaking, where particles that would otherwise be massless become massive because the vacuum itself is not perfectly balanced. Think of a pencil balanced upright on a table. In perfect symmetry it could fall in any direction, but the slightest nudge breaks that symmetry. The pencil falls one way. The Higgs field is that nudge in the cosmic balance, a choice the vacuum made early in the universe's history that determined how mass would behave from that point forward. And this choice has consequence. It means that the vacuum is not empty, not only because of zero-point fluctuations, but because it contains a permanent, persistent structure, a field that shapes the fundamental properties of matter. And, more than that, it means the vacuum energy itself includes contributions from the Higgs field. But here, once again, we meet a mystery. Because the energy predicted from the Higgs field alone, when plugged into Einstein's equations, suggests a contribution to the cosmological constant that is staggeringly large, much larger than what we actually observe. Which brings us back to the vacuum catastrophe. All the fields, electromagnetic, strong, weak, Higgs, contribute to the vacuum energy. And yet, the observed value is tiny. Something, somewhere must be cancelling, balancing, hiding the true scale of this structure. So while the Higgs field explains why mass exists, it also deepens the mystery of why the vacuum behaves so calmly. It's as if the universe is tuning itself, delicately and precisely, adjusting the knobs of the fundamental fields so that stars can form, atoms can bind, and life can breathe. And the Higgs field is one of those knobs, one of the most critical of all. Without it, the electron would be massless, atoms would not form, chemistry would not happen, the stars would not shine, The very structure of matter would collapse. So the next time you lift your hand or walk across a room, or feel the weight of your body, remember that resistance, that mass, is not just a property. It is a conversation between your particles and an invisible field that fills the cosmos. The Higgs field doesn't just touch the vacuum, it defines it. It sculpts the landscape through which all other particles move. It makes the universe feel real, solid, heavy, grounded. It is the silent architect of inertia, the invisible sculptor of substance, and without it, the quantum vacuum would be an echo with no form, a whisper with no voice. Chapter 18. Could zero-point energy cause inertia? We all know the feeling of inertia, the heaviness when you try to move, the resistance you feel when a car suddenly accelerates, or when you jerk your arm forward, the sense that something inside you wants to stay at rest. Inertia is not just mass, it is what mass does, the refusal of matter to change its motion. It is what makes physics predictable, what gives movement meaning. But for something so familiar, inertia is surprisingly mysterious. We know how it behaves. Newton wrote the laws. But why does it behave that way? Why does matter resist acceleration? Why does it take energy to make things move? Where does that resistance come from? It is tempting to say, because it has mass. But that simply shifts the question. What gives mass its resistance? And deeper still, what gives mass its meaning? Some physicists believe the answer may lie in the most unlikely place, in the quantum vacuum itself. Because the vacuum, as we've seen, is not empty. It is filled with fields. And those fields are in constant motion. A storm of tiny fluctuations, a sea of virtual particles, a dance of zero-point energy that never ceases. And now, imagine a particle, an electron perhaps, sitting motionless in that vacuum. It is surrounded by fields, yes, but it does not disturb them. It floats quietly. Now accelerate it, push it forward. Suddenly it begins to interact differently with the sea around it. It moves through the zero-point field, and in doing so stirs it. Like a boat cutting through water, it generates ripples. Like a charged object moving through a field, it feels a reaction. This idea that inertia may arise from a particle's interaction with the vacuum is not a new one. It has been explored by several physicists over the past few decades, from Andrei Sakharov to Hal Puthoff, all exploring a provocative question: is inertia a consequence of quantum vacuum fluctuation? Could the very resistance to motion, the essence of mass, come not from within the particle, but from its dynamic coupling with the structure of empty space? Sakharov, in particular, proposed something profound, that not just inertia, but even gravity, might emerge from vacuum interaction, that both are not fundamental forces, but consequences of deeper field behavior. Under this view, space is not passive, it is not just the stage, it is the medium through which matter must swim. And the resistance we call inertia is simply the drag of moving through the vacuum's energy. Now let's be clear, this idea is not mainstream, it is speculative, it is debated, it has not been proven. But what makes it compelling is that it reframes a known experience, inertia, in terms of something we already know exists. Zero-point energy. Instead of mass being an intrinsic quality, it becomes a relational one. It becomes a property that emerges when a particle interacts with its field environment, especially the vacuum, and that changes everything. It means that movement itself is not absolute, that every acceleration is a negotiation with space, that to move is to stir the vacuum, and that stirring comes at a cost. This is echoed, in a way, by the unravel effect, another strange consequence of quantum field theory. It says that an observer who is accelerating through empty space will perceive a warmth, a bath of particles where others see nothing. From the outside, the vacuum is cold, but for the accelerating observer, the motion stirs something loose. Virtual particles appear. Energy arises. Is this the vacuum pushing back? A friction? A glow? A hint that space responds to motion with force? If so, then perhaps inertia is not just a property, but a conversation between particle and field, between matter and the vacuum. This view resonates with a broader trend in physics, the shift away from seeing objects as isolated and toward seeing them as interconnected. No particle exists alone. It is always immersed in fields. It is always in dialogue with the vacuum. And that dialogue may be what gives us the world we know, a world where things move and resist movement, where effort is required to change direction, where mass means something because the vacuum won't let it mean nothing. Could zero-point energy cause inertia? We don't know. But if it does, even in part, it would mean that every time you lift your hand, every time you press against the earth, you are feeling not just your body's resistance, but the whisper of the entire universe pushing back. The vacuum would not just be a backdrop. It would be the partner in every motion, the unseen weight in every step, the true origin of all momentum. And then inertia, that silent, taken for granted property of mass, would become something astonishing, the signature of the vacuum's presence in you. Chapter 19. Virtual particles, real or illusion. They appear, flicker, and vanish before you even know they were there. They exist between moments, beyond measure, below detection. They are the breath of the vacuum, the ghostly flickers of the quantum world. We call them virtual particles, but what does that mean? And are they even real? In popular imagination, virtual particles are strange, rebellious things, particles that pop out of nowhere, exist for a split second, and disappear again into the silence of empty space. They are said to appear in pairs, one particle and one antiparticle, borrowing energy from the vacuum and giving it back so quickly that the universe doesn't notice. They are the explanation offered for so many of quantum field theory's odd effects: the Casimir force, the Lamb shift, the Hawking radiation around black holes, even the zero-point energy that fills all of space. But the word virtual is a trap. It sounds like fiction, simulation, a sleight of hand, and that's not entirely wrong, but it's not entirely right either. To understand virtual particles, we must first understand what they are not. They are not particles like electrons or protons. They are not things you can isolate in a lab or detect with a particle collider. They do not leave tracks in detectors or crash into targets. They do not exist in the same way real particles do. So what are they? They are calculations, artifacts of the math we use to describe interactions. They are terms in the equations of quantum field theory, intermediate steps in a process, not final results. When two particles interact, say an electron and a photon, they do not collide like billiard balls. Instead, their interaction is described through an infinite series of possible events, each involving temporary disturbances in the field. These disturbances, these virtual exchanges, are what we call virtual particles. They are ripples that briefly exist within the Feynman diagrams physicists use to map out interactions. They mediate forces. They carry momentum, but they are not directly observable. So are they real? That depends on how you define reality. If you require something to be measurable, then no, virtual particles are not real. They are tools, shortcuts, language. They exist inside our calculations, not in detectors. But if you define reality by effect, by whether something causes measurable change, then virtual particles have left their fingerprints everywhere. The Casimir effect, a measurable force between metal plates in a vacuum, can be modeled using virtual particles flickering in the space between them. The Lamb shift in hydrogen, A tiny change in energy levels emerges from the interaction between the electron and the froth of the vacuum, which virtual particles help us describe. Even the strong and weak nuclear forces are mediated by exchanges of virtual particles, gluons, W and Z bosons, that never appear as free particles, but whose presence shapes everything from atomic decay to the core of the sun. So in this sense, virtual particles aren't imaginary. They are the scaffolding beneath interaction. They are the unseen dance partners that make every collision, every emission, every force possible. But this is where quantum field theory demands humility. Because in the end, the fields are real. The vibrations, the excitations, the energy landscapes that fill space. Particles, whether real or virtual, are just how we perceive and measure changes in those fields. And so, virtual particles are not things, they are symptoms. They are the language of interaction, not the objects themselves. Think of them like shadows in a dream. You don't see them directly, but you feel what they've touched. You see the ripples they've left. They are not permanent, but they are not meaningless. And perhaps most hauntingly of all, their flickers are the whispering voice of the vacuum. They are the tiny disruptions that summed across all space give us zero-point energy. They are the imagined flickers that under extreme conditions, at the event horizon of a black hole, or in the expanding universe, can become real permanent particles. Hawking radiation, for instance, can be modeled as one virtual particle falling into the black hole, while the other escapes, turning an illusion into energy. Inflation theory suggests that quantum fluctuations, fueled by vacuum energy, were stretched into the seeds of all galaxies. Again and again, the math blurs into reality. So, are virtual particles real? They are not the kind of real you can bottle or weigh or photograph, but they are the kind of real that moves the world. They live not in detectors, but in the equations that predict everything those detectors will see. They are the grammar of the universe, silent but necessary. And without them, there would be no explanation for what we observe, no forces, no correction, no shift in energy, no mysterious pressures, no whispers in the void. So maybe that's the better question, not are virtual particles real, but can we understand the universe without them? And the answer again and again seems to be, even if they vanish before we can catch them, they leave the world permanently changed. Chapter 20. Quantum foam. The turbulence beneath space-time. At first glance, space looks smooth, calm, infinite. The stars sit still, galaxies drift. Planets turn in silent rhythm. From our human scale, the fabric of the universe seems like a vast flat sheet, stretched gently across time, untouched and unbroken. But that smoothness is an illusion. Zoom in far enough, far beneath atoms, beneath protons, beneath the trembling edge of the Planck scale, and space begins to change. It loses its stillness, it loses its shape, it begins to boil. This is the realm of quantum foam, not a metaphor, but a hypothesis, a picture of the very structure of space-time at its smallest scales. It is what some physicists believe the vacuum becomes when seen with ultimate resolution. Not flat, not empty, but foaming, bubbling, wild. The term was coined by John Wheeler, the same physicist who named black holes. He imagined that at scales around the Planck length, about 1.6 by 10 meters, the smooth geometry of space-time would break down. The uncertainty principle, when applied to gravity itself, would cause space-time to fluctuate wildly. And instead of a calm void, you would find a storm. Tiny, flickering structures, wormholes, loops, bubbles, topological knots, appearing and vanishing in time frames so brief they cannot be measured. Space-time itself would be uncertain. Not just empty space in time, but time and space themselves changing shape, constantly, chaotically, endlessly. This is what quantum gravity tries to understand. How do the rules of quantum mechanics, rules built on probabilities and fluctuations, apply to the very thing Einstein taught us to treat as geometry. How do you quantize space? How do you treat time not as a stage, but as a participant? In quantum field theory, we treat fields as quantum, the electromagnetic field, the strong and weak forces. But gravity, the force of space-time curvature, has resisted quantization. We don't yet have a complete theory of quantum gravity, but every attempt, from string theory to loop quantum gravity, must grapple with this concept, that at the smallest scales, space-time itself may not be smooth at all, it may be discrete. It may be stitched together from quantum units, individual, vibrating loops or strings, woven into a chaotic tapestry we call foam. In this view, nothing is not the absence of things, it is the bubbling cauldron beneath reality. It is seething, shape-shifting madness, tamed only when viewed from afar. The idea is radical, but it makes sense. If energy can fluctuate, why not curvature? If particles can appear and vanish, why not the very structure of space-time? And there are reasons to believe we may one day glimpse this foam. For example, some researchers have proposed that the speed of light might subtly vary over astronomical distances if space-time has a foamy structure, introducing a kind of quantum noise that builds up as photons travel. Others have suggested that gravitational waves, ripples in space-time itself, might carry imprints of this quantum granularity. And in black holes, where gravity becomes extreme and quantum effects cannot be ignored, the very fabric of the event horizon may be built from this restless foam. But for now, quantum foam remains theoretical, a picture without a photograph, a whisper without a voice. Still, the implications are profound. If quantum foam is real, then the vacuum is not just filled with fields, it is the field. Space-time becomes a medium, not a backdrop. Its behavior, its fluctuations, its turbulence become the most fundamental things of all. And suddenly, the zero-point energy we've been exploring takes on an even deeper meaning. Because it's not just energy floating in space. It's energy born of space. It is not just motion on the field, it is motion of the field. It suggests that the vacuum's energy may be tied, not just to particles and forces, but to the very shape of the cosmos at the tiniest scales. Think about that. When we look out at the stars, we imagine light traveling through silence. But what if every photon, every particle, every wave is surfing across a sea of hidden turbulence? What if every second of existence is balanced on a foam of boiling space-time? And here is where imagination becomes necessity. Because to unify quantum mechanics and general relativity, to understand the true nature of gravity, of black holes, of the Big Bang itself, we must understand this foam. We must look beneath the stillness, beneath the vacuum, beneath even the fields. We must ask, what is space, when there is no space left to zoom into? What is time, when it can no longer be divided? The answers may lie in the chaos, in the quantum storm beneath all calm, in the foam that bubbles when reality is viewed with eyes sharp enough to see everything. Chapter 21. The Casimir Effect. When nothing pushes, imagine placing two metal plates, perfectly flat, perfectly clean, a few nanometers apart in a vacuum. No air, no light, no particles, just empty space between them. You'd expect nothing to happen. After all, there's nothing there. No atoms, no molecules, no visible force. And yet, within that silence, something stirs. Over time, without touching, without charging, without heating, the plates begin to move. They push toward each other, as if an invisible hand were pressing them together. Gently, persistently, undeniably. This is not a trick. It's not magnetism, not static electricity. It is a real, measurable force, one of the strangest ever discovered. It's called the Casimir Effect, and it's caused not by particles, but by the absence of particles, not by something, but by nothing, or rather, by what we thought was nothing. Here's how it works. The vacuum, as we now know, is not empty. It's filled with quantum fields, fluctuating endlessly. Even in a vacuum, these fields jitter with zero-point energy, producing virtual particles, tiny ripples of energy that flicker in and out of existence. Normally, these fluctuations occur everywhere. They're evenly spread. But when you insert two plates closely together, you change the rules. Between the plates, only certain fluctuations are allowed. Only those with wavelengths that fit perfectly between the plates can exist. Outside the plates, all wavelengths are allowed. This creates an imbalance. There are more fluctuations outside the plates than inside, more pressure from the outside than the inside. And so, the plates are gently pushed together by the very vacuum itself. This force is tiny, almost imperceptible at human scales, but in the laboratory, it can be measured with extraordinary precision, and its existence confirms something profound, that the vacuum is not passive, that nothing has pressure, that emptiness can push. The Casimir effect was predicted in 1948 by Dutch physicist Hendrik Casimir. He envisioned this strange force while studying quantum field theory and boundary conditions. The idea that placing physical constraints can limit how fields behave. Decades later, it was measured in experiments that suspended small metal plates or spheres a few micrometers apart, confirming the theory. And what those experiments revealed is one of the most direct, tangible demonstrations of zero-point energy in action. This effect isn't just academic, it's real. It bends matter, it moves things, and in doing so, it raises questions that stretch into the deepest corners of theoretical physics. If the vacuum can push, could it also pull? Could it store energy in usable form? Could we someday extract energy from the vacuum? This idea has inspired science fiction for years. The concept of zero-point energy as a limitless power source drawn from the background hum of space-time. But reality is more complicated. The Casimir effect shows that vacuum energy exists, but harnessing it is another matter. The energy is bound into the structure of quantum fields, not something we can tap like oil or sunlight. Still, the very fact that the vacuum exerts force has far-reaching implications. In nanotechnology, the Casimir force becomes a practical concern, affecting how microscopic components behave, potentially causing parts to stick or malfunction. In cosmology, it serves as a clue, a laboratory-scale hint at how the vacuum behaves on vast cosmic scales. And in theoretical physics, it reminds us of the power of boundaries, because the Casimir effect emerges only when the vacuum is constrained. When space is shaped, structured, pressed into certain configurations, that's when the hidden pressure reveals itself. It's almost poetic. The vacuum is silent until you build walls around it, until you force it to show its hand. And then, quietly, insistently, it pushes. Perhaps this is the nature of the universe itself. It hides its deepest truths in stillness, but when shaped, when asked, when pressed, it answers. The Casimir effect is not a mystery anymore, but it is still a message. A message that the vacuum is not void, that silence is not absence, that every gap between things is filled with tension, potential, breath. And so, the next time you press your palms together, think of those plates. Think of the vacuum pressing back. Think of the nothing that pushes. And remember, even in the quietest corners of the cosmos, something is always moving. Chapter 22. Can zero-point energy be used as fuel? It's a dream that has danced in the minds of physicists, futurists, and storytellers alike. What if the vacuum, the infinite sea of jittering energy all around us, could be tapped like a cosmic battery? What if every cubic centimeter of empty space held enough energy to power a city, or a star, or a civilization? What if we could fuel the future with nothing? It sounds like fantasy, And in many ways it is. But like all the best science fiction, the seed of the idea is planted in real physics, in the zero-point energy of the quantum vacuum. We've seen the signs. The Casimir Effect shows that the vacuum can exert force. The Lamb shift proves it can alter atomic behavior. Virtual particles flicker in and out, feeding radiation around black holes, influencing cosmic expansion, sculpting the structure of matter itself. So if all this is happening invisibly, continuously, why can't we capture that energy? Why can't we build a machine that extracts useful work from the endless quantum froth? The answer is complicated. Let's start with the scale. The energy density of the vacuum, as predicted by quantum field theory, is enormous. Some estimates suggest that every cubic meter of empty space contains more energy than all the matter in the observable universe. It's a number so vast, it breaks our intuition. But here's the catch, that energy is not accessible. It's like the baseline of a deep ocean, immeasurably powerful, but perfectly uniform. You can't scoop a wave from flat water unless something disturbs it. And that's the problem. The zero-point energy is always there, but it's balanced. It can't be used the way a battery is used because there's no voltage, no gradient, no direction to flow. To extract energy, you need a difference. Hot to cold, high to low, full to empty. But zero-point energy is already the lowest state. By definition, you can't go low. This is not just a technical hurdle, it's a thermodynamic law. The second law of thermodynamics forbids perpetual motion machines, and any device that tries to extract energy from a system in equilibrium without input violates this. So the answer from mainstream physics is clear. You cannot extract usable energy from the vacuum without breaking fundamental laws. But not everyone stops there. Some physicists working on the edges of theoretical and experimental science continue to ask, are there loopholes? Are there conditions under which the vacuum can be coaxed into yielding its energy? One such idea involves dynamic Casimir effects, where mirrors move at near light speeds, altering the vacuum boundary conditions so rapidly that real photons are emitted. Experiments with superconducting circuits have mimicked this behavior. And yes, they did produce measurable photons from nothing. But the energy didn't come for free. It came from whatever moved the mirrors, from an external power source. The vacuum didn't give up energy on its own. It had to be stimulated. And even then, the energy gained was tiny, not remotely usable as fuel. Another frontier is Hawking radiation. Near the event horizon of a black hole, quantum fluctuations can be split apart, allowing one particle to escape and the other to fall in. The escaping particle becomes real, a form of energy extracted from the vacuum. But again, this process depends on extreme gravity, the kind found near black holes, not in your garage. Then there's the speculation, far outside the mainstream. Concepts like zero-point energy generators, field resonance machines, vacuum pumps. Ideas that promise limitless energy from the fabric of space-time itself. Most of these fall apart under scrutiny. Some violate energy conservation. Others can't be replicated. A few veer into pseudoscience. Still, the allure remains. Because the vacuum is not empty. Because we know it has structure. Because it leaves traces in particles, in forces, in cosmology itself. And that raises an even deeper question. What if the vacuum doesn't give us energy? But what if it already is the energy? What if the universe's expansion, the force of dark energy, the acceleration of space-time? What if all of that is zero-point energy at work? In that sense, we are already seeing the vacuum's power. Not in our machines, but in the shape of the cosmos. In the galaxies pulled apart. In the relentless growth of space-time. In the tension that makes stars burn and atoms bind. Maybe the vacuum won't power your car. Maybe it won't charge your phone. But it powers something larger. The structure of matter. The rules of force. The scale of time. So can zero-point energy be used as fuel? Not in the way we dream, not as an infinite, extractable power source, but as the engine behind reality itself. Yes, and maybe that's enough. Because when you realize that nothing is what keeps everything moving, you begin to see the vacuum not as empty, but as the wellspring of the world. Chapter 23. Why doesn't zero-point energy collapse the universe? It's one of the great paradoxes of modern physics, a silent contradiction, a cosmic whisper that refuses to make sense. If the vacuum is filled with energy, immense, invisible, constant energy, why hasn't it torn the universe apart? The numbers don't lie. Quantum field theory, with all its precision and predictive power, suggests that the vacuum should be dense with energy, trillions upon trillions of joules in every cubic meter of space, more than enough to curve spacetime into a tight knot, more than enough to cause gravitational collapse on a cosmic scale. And yet, the universe expands gently. Galaxies drift. Time flows. Why? To understand this, we must revisit one of the strangest forces in the cosmos, gravity, as described by Einstein's general theory of relativity. In Einstein's equations, energy is gravity's source. Wherever there is energy, there is curvature. Energy bends space-time. Mass tells space how to curve. Space tells mass how to move. And that includes vacuum energy. If the vacuum is truly buzzing with zero-point energy, then that energy should act like a gravitational field. It should press outward or inward. It should show itself through the expansion or contraction of the universe. But here's the problem. When physicists calculate how much vacuum energy exists, the result is catastrophic. A factor of 10 VMR, and it is by many orders of magnitude the most significant mismatch between theory and observation in all of science. This mismatch has a name, the cosmological constant problem. Because, in Einstein's equations, the cosmological constant is a term that acts like vacuum energy. It's the energy density of space itself, a constant pressure that affects the rate of cosmic expansion. Observations from supernovae, from the cosmic microwave background, from galaxy clusters, tell us that this constant is small but positive. It causes the universe to accelerate. It pushes galaxies apart. We call it dark energy. But the vacuum energy predicted by quantum field theory is vastly larger than the observed dark energy. So something, somewhere, is being cancelled. Somehow the zero-point energy of the vacuum, all those wild fluctuations, all those virtual particles, must be nearly perfectly balanced by something else. Something we don't yet understand. And this is where science meets its limit. Some theories suggest that positive vacuum energy is balanced by a negative contribution from gravity itself, a kind of natural cancellation. Others speculate that unknown physics, supersymmetry, quantum gravity, extra dimensions, could explain the balancing act. Still others invoke the anthropic principle, the idea that we observe a small vacuum energy not because it's common, but because only universes with small vacuum energy can form stable galaxies, stars, and life. In other words, we exist in this universe because this universe permits existence. It's not a satisfying answer, but it may be the only one we have, for now. What remains is a deep, unsettling truth. The zero-point energy of the vacuum is real. It is measurable in phenomena like the Casimir Effect. It contributes to observable physics, and yet its gravitational influence, the one predicted by theory, is missing. It's as if the universe knows how to subtract. As if reality holds a hidden ledger, balancing infinite energy with infinite emptiness. Or perhaps we simply don't yet see the full picture. Perhaps our theories, powerful though they are, only scratch the surface. Perhaps the true nature of the vacuum, of space-time, of energy, is still waiting to be revealed. Because if the vacuum really did collapse the universe, we wouldn't be here to ask about it. So maybe the better question is not why hasn't it collapsed, but what is holding it up? What principle, what symmetry, what elegant unseen law is keeping the most energetic nothing in existence so perfectly calm? We don't know, but in the silence between particles, in the tension between equations, in the quiet expansion of the night sky, we feel the answer: breathing. The vacuum holds, the universe floats, and for now, against all odds, everything remains in balance. Chapter 24. Does the vacuum define reality itself? Strip everything away: the stars, the dust, the atoms, the particles and their charges, the fields and their forces. Erase every object, every motion, every speck of matter across the entire cosmos. What remains? Most would say nothing, but physics whispers something different. It says the vacuum remains, not as an absence, but as a presence more fundamental than anything it once held. And that raises a staggering possibility. What if the vacuum isn't just what's left over, but what defines everything? In quantum field theory, the vacuum is not empty. It is the ground state, the lowest possible energy configuration of all fields. It is the default from which all particles emerge. It is the canvas upon which every law of nature is written. When we talk about particles, electrons, quarks, photons, what we really mean is excitations of a field, tiny ripples in the vacuum itself. The electron isn't a thing floating in empty space. It is space, stirred into a specific rhythm. Reality, in this view, is not made of particles. It is made of fields, and those fields are always there, even when perfectly still, even when nothing seems to happen. Which means the vacuum isn't just the background of reality, it is the substance of reality. Its structure determines which particles can exist. Its symmetry, or lack thereof, determines what forces operate. Its energy defines how space expands, how time flows, how mass behaves. The vacuum decides what is possible. In the early universe, when everything was hot and fluid and unstable, the vacuum went through phase transitions, like water freezing into ice. Those transitions reshaped the laws of physics. They broke symmetries, locked in masses, split the forces of nature into distinct identities. So even though we cannot see the vacuum, it has shaped everything we see. Even though we cannot touch it, it defines how matter touches everything else. In this sense, the vacuum is not the absence of substance, it is the memory of every choice the universe ever made. The imprint of creation, the hidden code beneath form. And this leads to a profound shift in perspective. We usually think of reality as being made of things, and space as the nothing in between. But in truth, the vacuum is not between things, it is the foundation out of which things arise. What you call a particle is just the vacuum vibrating. What you call a law of nature is just the vacuum behaving. What you call existence is just the vacuum expressing. And this is more than philosophical, it has real, measurable consequences. Change the vacuum, and you change reality. A different vacuum, with different field configurations, different symmetries, could produce a universe with no atoms, no light, no complexity, which means the universe as we know it is not inevitable. It is one possible expression of the vacuum, and perhaps not the only one. Some theories suggest that different regions of the cosmos, or different universes altogether, could exist with different vacuum states, different constants, different physics. A multiverse of possibilities, each shaped by a different version of nothingness. And in that idea lies both terror and beauty. Because if true, it means the most powerful creative force in the cosmos is not matter, not energy, not time, but the vacuum itself. It sculpts reality not with hands, but with symmetry and silence. It builds worlds not with tools, but with constraints and fluctuations. And from that infinite stillness, It draws out stars, minds, lives. So, does the vacuum define reality? More than that, it is reality. The bass note beneath every particle, the rhythm beneath every law, the eternal hum that sings the cosmos into being. And when you sit in silence, feeling nothing, hearing nothing, sensing nothing, know that the deepest parts of you, your atoms, your charge, your mass, are only possible because the vacuum holds them. And maybe, just maybe, what we call everything is only the way the vacuum dreams. Chapter 25. What does it mean if nothing is everything? We began with a question, a quiet one, a question whispered at the edge of knowledge, on the border between science and wonder. Is empty space actually full of energy? And over these chapters we've walked through the answer, slowly, patiently, peeling back the layers of reality. We've seen the vacuum not as emptiness, but as presence, not as silence, but as structure, not as absence, but as the invisible engine that powers everything. The vacuum holds zero-point energy, a trembling, ceaseless hum beneath all stillness. It allows virtual particles to flicker in and out, unseen yet consequential. It exerts force, like the Casimir Effect's ghostly push. It shapes atoms, affects light, gives rise to laws, and deeper still, it defines the canvas of existence itself. The fields that ripple into particles, the symmetry that gives us mass, the slow, dark expansion that draws galaxies apart. It is not what's left after matter is gone, it is what matter is built upon. It is not the thing between things. It is the thing beneath all things. And now, with all this in mind, we return to the final question. What does it mean if nothing is everything? It means we must change how we see. We are taught to value presence, to trust what we can hold, see, name. But physics reminds us that the most powerful truths lie beneath perception, that the stillest parts of the world are the most alive, that the calmest places carry the greatest storms. The vacuum, this so-called nothing, is richer than the stars. It curves space-time, it dances with fields, it births particles, it binds the rules of force and matter into a living cosmos. And if it were different, even slightly, we would not be here. No atoms, no light, no time, no questions. That is the true weight of the vacuum. It is the condition for everything else. Not a place, but a principle. Not a void, but a foundation. And what makes it most extraordinary is that it remains unseen. It asks for no credit. It never announces itself. And yet it shapes all things that rise from it. So what does it mean? It means that silence is not the absence of sound, that darkness is not the absence of light, that the vacuum is not the absence of meaning, but the origin of it. It means that in the places we think are empty, something sacred hums, something endless, something precise, something awake, and maybe, just maybe, that is the lesson not only for physics, but for us, that the things we overlook, the pauses, the quiet, the background, may hold the most power, that the emptiness we fear is not lifeless, but waiting, that nothing may be the greatest something we've ever misunderstood. Because in the end, the vacuum is not just the space the universe occupies, it is the reason the universe can exist at all. And when we finally learn to listen, to see not just the things, but the spaces between them, we will hear the soft, steady heartbeat of the cosmos, a rhythm that says there is no such thing as nothing, there never was. There is only the field, the flow, the foam, the trembling, the 0 point, the vacuum, and it is everything.